That's fine. There is no grading. So, so yeah. Hi, good morning, everyone. Uh, Welcome back on like fourth and final day of FIRE 2024. I think most of the people are still enjoying their breakfast, but I hope you have already had breakfast. So before we start, just 2 to 3 instructions for participants. We already covered the brief introduction about task description and dataset statistics. So I'll suggest you to emphasize more on your methodologies and results. Uh, we don't have any strict, but I'll suggest you to order the timeline like 5 minutes for each of the presentations, and then we'll take questions. Yeah. So with that, we'll start our first presentation from the Indian language summarization track, uh, titled Text Summarization for Indian Languages, Extractive Summarization Using Graph-Based Techniques, uh, by Ansh, Astha, and Philip. Please. You can do this now. Just have one more.
Hello, good morning, everyone. First of all, I would like to Good morning, everyone. First of all, I would like to thank the entire organizing committee and the track chair for giving us the opportunity to present our work on text summarization on Indian languages based on extractive summarization using graph-based method. So the proposed model is to develop an effective text summarization system which uses the novel text rank algorithm, and when integrated with LDA and dynamic damping factor, it enriches the vector embeddings so as to improve the quality of the summary generated. Moving on, there are various approaches for ATS that include extractive method, abstractive, as well as hybrid. So the extractive method that we've used, in that we use the graph-based technique where the top n sentences are selected. So the working of a model takes the input of single documents, which upon proper file conversion are passed to the data preprocessing phase. After that, the document term matrix is created, which maps the word frequencies to each sentence. Now, this document term matrix, when applied on LD algorithm, it creates the topic matrix. After that, the similarity matrix is built using the text rank algorithm. Further, dynamic damping factor is calculated based on the various factors which have been mentioned over here. Then that dynamic damping factor is passed on to the PageRank algorithm. After that, the LD and the text rank scores are combined and the generated summary is created, which consists of the top n important sentences. Further methodology will be explained by Ansh Vora.
Thank you. So the first step in our model involves data preprocessing. So TextRank is an algorithm that works at the sentence level, and it calculates the word overlap between various sentences. As a consequence of this, during the preprocessing phase of the text corpus, we need to perform sentence tokenization as well as word tokenization. Since it is an extractive summary generation technique, thus removal of stop words as well as POS sentence tagging, that is parts of sentence tagging, can also be performed. The POS tagging is, however, optional. The next step is using the latent Dirichlet allocation for topical modeling. The latent Dirichlet allocation is a statistical model that is used to gain the semantic information about a document and find the latent topics that are present in the document. So this assigns, the LDA basically creates a topic matrix in which every sentence is assigned a score according to the probability of the topic which is present in that sentence. This is done using the document term matrix, which by applying LDA is converted into the topic matrix. Then we apply the text rank algorithm. The text rank algorithm is the novel 2007 text rank algorithm, which is based on the original PageRank algorithm, in which the similarity between sentences is calculated as the cosine similarity between the word overlaps. In this, we use a damping factor, which is denoted by alpha in the given formula. This damping factor is generally assumed to be 0.85. So this means that when the summary is being generated with an 85% probability, a connected node will be used in order to generate the next sentence. And with a 15% probability, a random node will be chosen. However, this has one major drawback, that in a lot of sentences where the topical spread is very high, in that case, the connectivity between nodes is lower. So if we stick to one node, it will only follow one particular predefined path according to that node. In order to prevent this, the damping factor can be dynamically adjusted in order to reflect the given text corpus. So we calculate the dynamic damping factor using these 5 factors. The first is the node connectivity factor. These all have been normalized. The formulas over here are all the normalized factors in order to bring them between values of 0 to 1. The node connectivity factor basically shows us the connectedness between various sentences of the document. So as the connectedness increases, we can have a lower dynamic damping factor. The entropy factor is basically just showing us what is the distribution across the topic, across the various topics in the document. The variance factors basically calculates the variance of the two matrix which we generate, that is the topic matrix as well as the text rank matrix. The length factor, again, we assume that longer articles tend to have more diversified content. So that is why the fourth factor is length factor. And lastly, we have the number of topics, which is again modeled using the LDA algorithm, which we had used earlier only. Thus, this is the final model formula, which will be explained by Rini.
Thank you. So, as mentioned, this is the final model formula for our dynamic damping factor based on different parameters like the connectivity, entropy, length, topic, and variance. And as you can see, the weights for each of these different factors have been come up with the high level of data pre-processing. And this is the final dynamic damping factor, which when integrated with LDA and text rank gives us our final proposed model. So moving on, let's move on to the different results of how our model is comparing to the different data sets of the ILSIM. So regarding the train, the cross validation, and the test data set. We also found out that our model compares really good when the number of documents increase. So we have already also tested it on more number of documents with additional data sets. Two such examples being the Webis corpus dataset, which consists of 266 documents and news articles. And this is how our text rank model compares to the original text rank model. We also tested it on the BBC extractive summary dataset. And as you can see, the Rouge F1 score of our integrated model compared to the text rank and how better the scores are. We didn't just stick to the dataset. We also tested our dataset across different comparison models, like the Falcon model, the MPT, and the OpenAI's ChatGPT. And these are existing models in the world today, and our model compared to all the different models in the world today. So this is how the comparison scores are. Moving on, let's giving you a brief conclusion. We explored a new approach of text summarization by integrating the original text rank algorithm with the latent Dirichlet allocation for topic modeling. We used semantic information extracted through the LDA to capture the different various themes in the document. We also integrated a dynamic damping factor to capture the nature of the input text and the topical coherence of a document. Also, it mentions and has a perfect representation balance between all the various topics. So the text rank algorithm integrated with LDA and the dynamic damping factor gave us significant improvements over the original text rank algorithm. So this was our proposed model. Thank you.
Thank you, Ansh. Can you go back to previous slide where you compared it with LLMs?
Sure.
Like last.
Yeah.
Okay. So this is root scores, right?
Yes.
And this is a zero shot setting, or you are doing ICL? I mean, this is zero shot summaries, or like you use some examples like for in context learning.
So basically, we use this on the CNN Daily Mail dataset in which we were given reference summaries.
Okay.
And these models also we tried out with them for 25 articles.
Okay. No, so like, do you provide some examples like this is what the summary looks like in prompt, or like while generating summaries, do you just say that summarize the above article, or do you provide some examples like this is what
No,
something-
so this is basically an unsupervised approach. So you don't
Okay.
need to give any additional
Okay.
data. That is why even the train and the cross-validation data set which we have given for ILSAM,
Okay.
even that we could actually test it out directly because there's no need to train our model.
Okay.
It is an unsupervised approach. It is
So,
extractive.
yeah. And you are using LDA, right?
Yes.
Yep.
So, like, did you try looking at generated summaries manually?
Yes.
So, how is the overall coherence?
The coherence as well. There is a good flow between there. There is the semantic information capturing is much better.
Okay.
So what happens with the original text rank is, for example, it cannot understand the dependencies very well. So
Right.
if we give A depends on B,
Right.
and if we give B depends on A, given normal text rank, it will basically assume both of them are similar because it checks the recall and precision and things like that. But what LDA is doing, it is also being able to map this dependency pretty well. So that is why the coherence which is there, which is even reflected in our BERT scores,
Okay.
which is showing that the coherence of our model is much better because LDA is understanding the semantic information behind it.
Okay. And do you have any observations like when there is a shift in topic? Because like some article in the test data might not be there, like, I mean, overall topic can be different, right?
Yes. So that is why majorly we've stuck in our data sets, we've majorly stuck to news articles in which the overarching topic is kind of similar. So that is when our model is performing the best. One thing that we observed, which was mentioned, as Rinit mentioned, that when the summary has to be generated, when the summaries are longer, like 20% of the original article length, so the number of sentences the summaries are longer. At that time, the semantic information capturing makes the overall quality of the summary better. That was our first observation. Our second observation was when the input article is smaller. In that, in terms of either the topic distribution which is there, in that case, our summary quality is a little bit inferior because there is not enough semantic information to be mapped out. In such cases, even a normal text rank algorithm will give similar results to us because there is no relationship between topics which can be explored as such. So this method just becomes, since it incorporates LDA, it is a computationally expensive method. So it just becomes computationally expensive without any significant increase in results.
Yeah, thank you. Yeah, I think that's all. Any other questions? Do we have any questions from the people joining us virtually? Yeah, okay, thanks.
Thank you so much.
So, yeah, next we have is another paper titled Enhancing News Article Summarization Through Post-Processing Techniques from Fatima, who is joining us virtually. Fatima, are you there?
Yes, sir.
So, yeah, just try to stick to the timeline of 5 minutes. Just present the methodology and results.
Okay, sir.
Probably you can start by sharing your screen. Yeah, thank you.
Actually, it is showing that host disable the participant screen sharing. Could you please enable?
If you're trying to say something, I don't think we can hear you. So can you
Hello?
please check?
Am I audible? Is my screen is visible, sir? So, good morning to everyone present here. Our paper entitled "Enhancing News Article Summarization Through
Fatima, if
Post-Processing."
you are like speaking something, I think
Yes.
it's not audible. Can you check your mic?
Hello, is my voice audible?
Yes, it is.
Okay, let me.
You're still not audible here.
Hello. Is my voice is audible, sir, now? Hello.
Yeah, it's audible now. Thank you.
Okay, sir. So, a paper entitled Enhancing News Article Summarization Through Post-Processing Techniques. So, myself, Fatima Fairoz from Tyagaraja College of Engineering, Madurai. So, this study addresses the challenges of repeated words in multilingual news article summarization, particularly for low resource Indic languages such as Tamil, Telugu, and Kannada. So, using the post processing techniques such as repetition avoidance, sentence length control, and headline integration, we fine tuned versions of Indic bar tests and T5 base models. And the results indicate significant improvements in summary quality and the linguistic adaptability. So, summarization of news article is crucial for efficient information processing, especially in low resource Indic languages. While the advancements in neural summarization models have improved summary generation, challenges such as repetition and lack of coherence persist. So, this work explores post processing techniques tailored to address these issues in Tamil, Telugu, and Kannada, and additionally, we also did for English. So, the objective and scope of this work is focused on enhancing the multilingual summarization by applying tailored post processing strategies aiming to improving the summary quality while adapting the structural nuances of each languages. So moving on to the related works, let me skip this due to the limited time. And the study uses the ILSIM 2024 dataset, and here is the training samples, validation, test sample split that we have used. So moving on to the models used. So for Tamil, Telugu, and Kannada, we have used IndicBAT SS. We have fine-tuned that, which is basically an MBAT architecture, and it is um, trained on corpus over 452 millions of sentences and 9 billion tokens. And this is specifically designed for 11 Indic languages, which includes Tamil, Telugu, and Kannada. So, moving on to the next one, that is T5 base, which is a powerful model, text-to-text transformer model designed for a variety of natural language processing tasks. We have fine-tuned it for English. So, moving on to the summarization techniques, our work basically split into 3 runs, which is the first run, which is focused on repetition avoidance, and the second run, which is focused on repetition avoidance as well as sentence length control. The third run, which is focused on repetition avoidance and sentence length control, and we have integrated headline. So, let us see one by one. So the first run, which is focused on repetition avoidance, we have used a technique called diverse bean search, in which we have 6 beans divided into 3 bean groups. So diversity penalty was set to 0.7 for and the no repeat n-gram size was set to 3, and we have incorporated a repetition penalty, and which have significantly improved the quality of the generated summary and reduce the redundancy while preserving the article meaning. So moving on to the run 2, repetition avoidance as well as sentence length control. In run 1, we saw that the summary length was too long, so we just employed a sentence length control parameter in run 2. So in that, we have set the sentence length control to 2 sentences, and the summaries were informative and limited to 2 sentences and non-redundant. So moving on to the third run, we have employed repetition avoidance, sentence length control, as well as headline integration. So we have integrated the headline during the pre-processing to enrich the content. So which this run focused on summaries anchored to the article cycle, so limited to the 2 sentences, and which is free from redundancy. So moving on to the results, so this is the results of using route scores. So we can see that the run 1, run 2. So we can see that the Tamil run 1 has comparatively more than Tamil run 2 and 3, and in 4 of the languages, run 1 stayed at the top, so which are highest route scores. And moving on to the BERT score, still run 1, which uses the repetition avoidance technique, stays at first, and we have secured top scores in Tamil and Kannada and Telugu, and top second in Tamil and English. So, in moving on to this BERT score FN, let's compare this, and here we can see that the plot of the BERT F1 score using across all the four languages. So, in which we can see that in some cases, Run 2 is also giving some which is closer to Run 1. So, even though Run 1 was always secure at the top, secure the top place. So, moving on to the results discussion, post processing significantly enhances the summary quality but requires language specific adaptation. While repetition avoidance is effective across all languages, techniques like heading integration need further refinement for Indic languages. So, this is what our findings is. So, on conclusion, this study demonstrates the potential of tailored post-processing techniques for improving multilingual summarization. So, the future research should be focused on expanding techniques to more languages and conducting human evaluations for deeper insights and exploring cross-lingual summarization. So, these are the references and open to your questions.
Yeah, thank you.
Yes, sir.
Yeah, so thanks a lot. I think with due to time limits, we'll move to next presentation from Kaushal. Title: Accessing Factual Accuracy in Machine-Generated Cross-Lingual Summaries Using Logistic Regression and BERT. Kaushal, are you there?
Thank you, sir.
Yeah, is Kaushal there? Anybody from Kaushal's team? Okay. So is Chaitanya there?
Yes, I'm there.
So probably you can move to your presentation now.
Yeah.
Start by sharing your screen.
Just give me a second.
Sure.
Please let me know if my screen is visible.
Yes, your screen is visible.
So, hello all. My title is Abstractive Summarization of Large Articles in Hindi Language using IndicBART. So, my approach for this share task is limited to summarization of large news articles in Hindi. And the approach that I took was essentially comparing multiple pre-trained well-known models that were available and customizing them so as to customizing pre-processing techniques so as to maximize performance for them. So essentially, I started off with comparing three models. First was IndicBERT, the second was MT5, and the third was IndicBART. And I landed on IndicBART for the following reasons. So basically, for IndicBERT, what I discovered was initially that the tokenizer for IndicBERT itself was not particularly suited because it was actually stripping off vowel characters. For example, the matras in Hindi language were being stripped off. So I ruled that model out from the in the pre-processing stage itself. And for MT5, it's actually, as I've mentioned, it's the data training corpus is spread across 100 plus languages. So the training results for MT5 post the chunking process that I have applied, which I will explain later, the results were not that promising. So I further settled down for IndicBAT. So before I move on to my methodology, essentially the core issue that I faced was because of resource constraints, I was constricted to using MT5 symbol, which has
Interrupt.
a maximum input token sequence length of 1024 token. And as you can see in the graph here, some of the token lengths, post tokenization of the news articles were well above 2000, 3000, stretching even perhaps to around 5000 tokens. So it was essential to come up with a pre-processing technique that allowed uh, usage of these models in spite of the input size being as large as it is. So I implemented a chunking approach essentially, which basically I divided a single article into multiple chunks. Where I made sure that each chunk was below the length of 1024 tokens. And it was important to make sure that no chunk was uh, cutting a sentence in half so as to maintain semantic meaning, essentially. So I basically split each chunk and maintained the common ID which was provided in the data set. I trained I trained the model. Uh, I trained the model with these by providing these particular chunks, evaluated them against the root scores, and then recombined these the generated summaries and uh, uh, evaluated them against the root scores so as to complete the training process. So uh, post the training process for IndicBAT, these were the results that I obtained. So as you can see, the road scores for the Hindi language summarization. The Rose 1 score is 0.34 and the bird score precision is 0.72. So post that, I mean, there is a lot of scope for improvement here, of course. There, the semantic meaning here, because you're splitting chunks without really considering the semantic relation, uh, it might probably be more suited to perhaps implement an ensemble approach where you're probably implementing some sort of extractive summarization on individual chunks so as to reduce the size of those individual chunks and then further implementing an abstracted model on top of that so as to give a better quality summary. So for now that's the current scope of the approach. Open to questions.
Yeah. Thank you, Chaitanya. If there are any questions. All right, then we'll move to next presentation. Is Tanisha here?
Hi, I'm Soumya and I'll be presenting on behalf of Tanisha.
All right, no issues. Just try to stick to 5 minutes timeline because we have a keynote in some time.
Okay, yes, will do. Can you see the presentation?
Yes, we can.
Okay. A very good morning to one and all present here, and thank you so much for being here. It's a great pleasure to present our work on text summarization models and the performance across English, Tamil, Bengali, and Gujarati. The research investigates the various techniques from frequency-based methods to advanced transformer-based models to evaluate the effectiveness in the different linguistic contexts. So let me start by introducing the problem that we are addressing. We are trying to perform text summarization, which is important in natural language processing, where the goal is to reduce a text into a shorter version while maintaining its meaning and essential content. The data set that we use is provided by ILSUM, and it consists of article headline pairs for Bengali, Gujarati, Tamil, and English with over 15,000 records. First, before training the data, we performed a few pre-processing steps. This was done by removing the unwanted characters, spaces, and punctuation. We normalized the text, that is, made everything in UTF-8 encoding and converted it all to lowercase in order to ensure consistency. And we focused on quality for better summarization performance. We used a variety of different models in our research, ranging from frequency-based models to transformer-based models, and several language-specific adaptations. First of all, we use some frequency-based models. This classical model operates by extracting the most frequent words from a text and assuming that these words are the most critical for generating a summary. While it is extremely simple, it has shown effectiveness in certain languages like Bengali and Gujarati. MT5 is a more advanced model, where MT5 is a multilingual version of the T5 architecture. The T5 architecture leverages a transformer model that is designed to handle multiple languages. And for Tamil, we use this specially trained model called the MT5 Tamil. Now, in order to evaluate our findings, we used the Rouge scores. We used the Rouge 1, Rouge 2, and Rouge L scores mainly. Rouge 1 looks for unigram overlaps. Basically, unigram stands for single words. This is a basic but critical measure of content coverage. For English, Gujarati, and Bengali, the frequency-based model performed the best, with relatively high Rouge 1 scores. This shows that the simple word frequency approach is effective in these languages, especially when identifying key terms. On the other hand, for Tamil, the MT5 Tamil model outperformed the others, achieving a Rouge 1 score of 0.0963. This shows that it's highly superior in understanding Tamil's language-specific intricacies. Rouge 2 talks about the bigram overlap. This is the overlap between the pairs of consecutive words. This measure helps us assess the coherence and the flow of the generated summary as it looks at the word relationships and context. Again, the frequency-based model showed solid performance in Bengali and Gujarati, but the MT5 model excelled in Tamil. The frequency-based model struggled in Tamil, showing that the need for more sophisticated methods to maintain the coherence in this language. Rouge L, on the other hand, checks for the longest common subsequence. This looks at the generated and the reference summaries and searches for the longest common subsequence, that is the LCS. This is important because it evaluates the structure and the order of the text, providing a more comprehensive measure of the coherence and the content retention. For English and Gujarati, once again, we see that the frequency-based model continued to show strong performance, whereas MT5 showed the highest reviews for Tamil. Now let's move on to the performance results in each language. By evaluating the models on the Rouge 1, Rouge 2, and Rouge L scores, we were able to attain insights into the various models' effectiveness in terms of content coverage, coherence, structural alignment with the reference summaries. As you can see from the presentation, the frequency-based model outperformed all the other models for English, Gujarati, and Bengali, whereas for Tamil, the MT5 Tamil model attained the highest root scores. The frequency-based model showed strong performance, particularly in Rouge 1 and Rouge 2 scores for English. The model identified the key terms well, yielding summaries that preserved the essential content. However, it struggled with contextual relationships between the words, which led to relatively shallow summaries. Nonetheless, the simplicity of the model made it fast and efficient, and it remained a strong competitor compared to the more complex models. For MT5 showed a decent performance in English, but the frequency-based model still outperformed it slightly in terms of the Rouge 1 score. This may be because the MT5 didn't leverage the simple word frequency approach, which worked well for English, but it did perform well in preserving the overall structure of the text. So we can see that the frequency-based model is highly effective as it focuses on the word occurrences, and it is capable of distilling the key information efficiently, quickly. So it is highly suitable for morphologically rich languages, especially like Gujarati and Bengali. And we can see that it is suitable for identifying the high frequency terms and extracting the key content of the para. The MT5 Tamil model was tailored for Tamil, and it helps improve the contextual understanding for better Tamil summarization. The frequency-based model has certain limitations, as we discussed earlier, and it is important to note that due to a lack of sufficient training data, it may be difficult to obtain higher results for low resource languages as per our study here. The transformer-based models have, like MT5 Tamil and so on and so forth, have a variety of advantages. These have excel in the understanding of relationships between the words, sentences, and overall text structure. And so they are particularly useful for languages with complex syntax like Tamil. They tend to generate more coherent summaries that preserve the meaning of the text while maintaining the logical progression. Models like MT5 are capable of handling languages simultaneously, making them highly adaptable. However, these transformer-based models have their own set of challenges. These models are computationally expensive, requiring significant resources for training and inference. While transformer models tend to perform well across languages, they still struggle with the low resource languages or languages with limited training data, as seen with IndicBERT. In the future, we realize that there are several exciting opportunities. By combining the strengths of the frequency-based model with the contextual power of the transformer models, we can create hybrid models that leverage both approaches, leading to summaries that are both accurate and meaningful. It is possible to incorporate neural networks with user feedback loops in order to further refine the models, improving the depth and quality of the summaries over time. And it is also important that we should focus on improving the performance on models on low resource languages by creating more efficient methods of training with limited data.
Okay,
In-
that's the time.
Yeah.
Okay. So do we have any questions here? In the online meet, do we have any questions? Okay, so now we can move to the next presentation by Rishika Jain. Sorry.
Yes.
Rishika, you can present your screen and start the presentation and try to maintain the duration of 5 minutes.
Yes. Is my screen visible? Yeah. Good morning, everyone. I am Rishika Jha on behalf of my team and co-authors Rakshit Ahuja, Sainik Kumar Mahato, Monalisa De, and Dipankar Das. Today, I will be presenting our research on enhancing accuracy in summarization for Indian languages. As we know that text summarization is a vital area in natural language processing.
Ishika,
Which
sorry for the interruption. I think
yes.
we have a very strict time limit. I suggest you to focus on your methodology and results.
Okay. So let me tell you that we have participated in both the tasks. That is the task one for the summarization and task two where we have to detect the factual inaccuracies in the machine generated summaries for the Hindi and Gujarati language. So we did that and here's the methodology. For the methodology, we used the T5 small model that's especially for the English language. For the text processing, we employed the T5 tokenizer for converting text to model compatible format using sentence space algorithm. And for the summarization function, we developed to concise summarize with specified length, constraints, and penalties. Here is a model. This is the methodology for the task 1. And for the task 2, our methodology was first the feature extraction. We have vectorized text features using the TF-IDF splitting data into training and testing subsets. We have built various classifiers, including logistic regression, random forest. Actually, we have tested among 6 different machine learning algorithms, and we have chose the best among them. And for the assessment, we have noticed that the logistic regression is giving the best result, so we have finally submitted that. So here is a flow chart for our methodology of task 2. Moving on to the results. Here are the rankings that were given by the ILSM. The rank 4 for the task 1 using the root metric, and rank 7 in the task 1 using the BERT metric. For the task 2, we achieved the rank 4 in the Gujarati language and rank 6 in the Hindi language. And both were evaluated on the F1 metric. So moving on to the next slide, here is future scope. For future scope, we want to explore few shot learning and larger models like GPT-4, implementing machine learning algorithms for factual inaccuracy, like more machine learning algorithms. And the goal includes optimizing fact encoders and using advanced machine learning techniques to increase the reliability. And here is the conclusion. We addressed the challenge for multi-label error classification in machine-generated summaries, focusing on misinterpretation, fabrication, false attribution, inaccurate quantities. For task 1, our best results were achieved using the T5 small model. And for task 2, we involved the classifying inaccuracies and logistic regression. As I mentioned earlier, it proven to be the best. And here are the references.
Thank you, Rishika.
Thank
Uh,
you.
So next we have a presentation from Sangeeta Singh. Is Sangeeta or anybody from her team is here? Yes. What is the query? No. Yeah, is Kaushal there?
It's Kushal, and I'll be presenting on behalf of him.
I apologize.
Yeah.
Yeah.
It's for the team IV Sum, right?
Sorry?
For the team IV Sum.
Yeah.
Yeah, I'll be present.
All right. So yeah, just try to stick to the 5-minute timeline. We're running
Yeah.
out. So just focus on methodology and results because everything else is covered.
Sure.
Yeah, let's start. Yeah, I think start the
Yeah,
presentation.
am I audible? Sorry,
Yeah, you are
I
audible.
had a network issue.
You are audible.
So the task that we undertook was to detect the kind of factual incorrectness in machine-generated summaries, in machine-generated cross-lingual summaries. This is the introduction. Now, the data set that we were given consisted of the training and test data set. The training data set had a lot of attributes, such as the source article, along with the incorrect summaries in multiple languages, and the correct summaries as well. However, the test data set that we were given with had real world conditions where only the English articles and their Hindi or Gujarati summaries were given. We started, so this is basically the number of samples in each data set. We had to classify the summaries into any one of these factual incorrectness or as correct, which is misrepresentation, inaccurate quantities or measurements, false attribution, and fabrication. So we started off with logistic regression. We decided to go with logistic regression because we thought it would be good to start off with a baseline model, such as logistic regression itself. And we did this by pre-processing the text. We did the pre-processing by combining the English article along with its Hindi or Gujarati summary. Then we used TF-IDF vectorization to convert the text into numerical features. We did this because it's important to capture the importance of terms. And finally, we label encoded the error types for classification. And after carrying out the normal this is the methodology for the same. After carrying out the normal logistic regression, we the exploratory data analysis made us realize that the number of correct labels in the data set that was given to us was high. So it needed class weighting. This modification helped us by helping us to pay more attention to minority classes and improving its ability to identify error types like fabrication and false attribution. This is the methodology for the same. And now we did logistic regression for the Gujarati dataset. For the Hindi dataset, we thought we'd go with a transformer-based approach. And for this, the texts were tokenized using word tokenizer, and the inputs were padded to a uniform length of around 512 tokens. We fine-tuned this model over 3 epochs, optimizing parameters such as the batch size, learning rate, and the weight decay. And in order to further improve the performance of the model, we used BERT with focal loss as well, because as I mentioned earlier, the number of correct labels were very high compared to the false labels. And this strategy emphasized harder to classify samples, ensuring that the model did not overlook challenging cases like fabrication or false attribution. And by addressing class imbalance through focal loss and fine tuning, we achieved significant improvement. So and this is the result for the same. For the Gujarati dataset with logistic regression with class weights, we got an F1 score of about 0.33. And for the Hindi, for BERT with focal lot, we got the highest F1 score of 0.3426. And this is the result given to us by ILSIM. We were ranked 1 in both of the datasets. So yeah, and for concluding, something for conclusion, something that with classmates worked best for us. That's it. Thank you.
Okay, so we are open for questions. Anyone, any doubts, any queries? Okay, thank you so much for your presentation, and we'll go ahead with Sangeeta Singh. Anyone in online participant, anyone on behalf of Sangeeta Singh? Okay, so we'll have a tea break of 15 minutes. We'll have a tea break of 15 minutes and of 10 minutes. We'll have a tea break of 5 minutes and we'll come back at 10:10. Okay, thank you.
ये लोगों के चालू कर दूंगा मैं।
Okay, Sangeeta, you can start your presentation.
You can start.
Like anyone from online participants, can you confirm if we are audible to you?
Yes, you're audible.
Sangeeta, your time slots, it's like just now you can present your paper just now. You can start now and you have like 5 minutes of time slot. Thank you.
Hello, Sangeeta. Are you there? You are not audible. Now you can say something.
There is one more present. One more. Ah, 5 minutes.
Sangeeta, are you there? Your voice is not audible. Can you say something? Hello. You are unmute. You can say something. Can you leave and rejoin us? Leave the meeting and rejoin us.
Sangeeta, we have a keynote starting soon. So I think we have to skip your presentation as of now. We will see if we can try to reschedule it some other time. So yeah, thank you and sorry for the inconvenience.
Is this yours?
No, it's a second. I sent yesterday.
This one?
No, that's it.
Okay. Hmm. Okay. Yeah.
Okay. Thank you.
Yeah. Hi, good morning again, everyone. So now we have a keynote address from Professor Thomas Mundell from University of Hildesheim. The title is on hate speech detection, basically platform needs, detection technology, and regulation. So, yeah.
Okay, yeah. Thank you very much, Ray. Thank you very much for the invitation to the conference organizers. And let's get started. So this will give a brief overview of hate speech and the broader context. But first, maybe some of you might have a question. Where is Hildesheim? So I will solve this soon. The brief CV of mine. I'm there for almost over 20 years now in Hildesheim, and it's located all pretty much in the middle of Germany, a little bit to the north. So you can easily remember where that is. And we got also some very nice old buildings and even some World Cultural Heritage churches. And for example, these bronze doors from around 1000 that are each 1 ton. And they still don't know which technology was used to create such intricate bronze door which is 3-dimensional. You cannot see well on this image there. But anyway, let's move to the current topics. This is what we presented pretty much in HASOC, thanks to Shrey, for example, and many other people. We had a classification task for hate speech at the FIRE conference for 6 years now, actually. And what we do pretty much is we have a data set, we have a classifier, there is a result, and then we declare the best system, and we're happy. And next year we start all this again. And we would call this an AI system nowadays because we use some deep learning technology. Is it some problem? Zoom doesn't listen to us. So. So let's resume. Yeah, so this is the binary classification task we're doing, and we're repeating that, and then we know what is a good system, and we keep doing this. But if we look at this, we only take actually a very technical perspective, and we look only at a small part of the problem and of the issues that are involved here. For example, now we have the annotators who look at the data set and do the annotations. And later in the talk, we will see what are some of the biases that happen, because we have people with their knowledge, people with their attitudes and their understanding, and this will all influence our AI system. On the other hand, we have a concept of hate. What is it? What do we understand when we talk about hate speech? Do we also mean cyberbullying and whatever? There are different concepts. And well, we simply declare one very short in our HASOC papers and say, okay, let's try to be broad and so on. And we don't know if the concept that we think is also a concept that the annotators have. There's some publications that say, oh, even if we train the annotators to get a common understanding of hate, they do the same job. They do whatever they want and what they think is hate. So that's very hard to govern. So there's lots of non-technical issues that we cannot. If we just look at this, we don't have control over these variables, but they have a lot of influence on us. Just one example. And of course, this all happens in a much larger space, right? There's many other players. I'll put some of them. We have our AI engineer, maybe. We have the annotators. In reality, we have users of social media systems. They are posting this hate, right? Or they are victims of this hate. We don't look at them and we don't consider them. We have a data set. We are very happy that we have a data set of a few thousand tweets, but there is a real data somewhere. There is the whole data somewhere, and we have no idea about the representativeness of our data. Very little, actually. We have a lot of biases when we extract that. We search with certain terms and so on. Our data set has issues. The annotator have bias issues. We get lots of different biases. And so far, I think at least we have very little methods, very little scientific method to measure this bias. What is actually a good data set? Inter-rater agreement is commonly used, but we have no idea about the difficulty of the specific tweets, and there might be a natural higher inter-rater agreement, a lower inter-rater agreement for certain tweets. So we don't know what's happening here. Then there is, of course, a cost involved for platforms. If they involve such systems, they might have their interests. Consider acquisition of Twitter by a very powerful person who wants to influence the society with his tool. We have also civil society organizations, fight hate speech, who have agendas and try to improve society from their point of view. They will integrate. Now they are, for example, in the new Digital Service Act, I will talk about at the end. They have been really mentioned and given a role finally as trusted flaggers, right? There's actually a name for this now, and they have certain privileges. We have legislators, right? The EU has passed several legislations about online media, online markets. Yeah, and all of this affects, of course, the society. What can we see? What happens? Legislation might come up and redefine this concept. That's why I made this box a little larger. Now, the real concept of hate, many people have different concepts, and it's much larger of what we think in our shared task. And our legislator do some issues. We think, oh, platforms should do much more. Yeah, but what should they do? Blocking, is that efficient or not? And at the very end, I will talk about two studies that show how does blocking and other measures, what are their effects? What can we say empirically about that? We're just saying, oh, they should do this, they should do that, but what is it really positive? We have two perspectives here, two extreme perspectives. One is the techno-optimism, also techno-pessimism, right? Techno-pessimism, let's start with techno-pessimism, is, oh, these new tools, social media, they just make society worse because they bring new tools. We have more polarization and all of that, and more hate, and we see the hate forever. Now it's not just spoken and forgotten, but it stays there. So this is bad for society. Techno-optimism would be, well, there might be some issues like hate speech, but let's just find another technological solution, and technology will solve these issues and make our life better. And the truth probably somewhere in between, but that's how the societies manages technology, and we will see. So quick overview now of this, after this broad introduction. I will quickly talk about first hate speech, also from a linguistic point of view. I work a lot with linguists, and then we briefly mention what we do in the shared task, but we did it already earlier, so very quickly. I'll talk about some of the biases that I see when we do such things, current topics, regulation, the different laws that I'm aware of at least, and some, as I mentioned, effects, what actually happens when we block channels. Let's start with hate speech. I forgot the disclaimer that Ray had put in his talk. Please, there could be some nasty content now, some hateful content. Be aware of that. This will be typically misogynist hate speech. Affects quite a big part of the society. 50% are female, so they could be affected, and not like, of course, like misogynist hate speech. And this is just some examples that we will find. I have to check time. You give me a warning, time warning. And we also have, of course, problematic. Some things you say, okay, yeah, I can have an opinion that something is negative, that is okay, that could be freedom of speech. Now, even if I don't like it and don't agree, it's not necessarily hate speech. It's also used sometimes as a gender term. Then we have some very clearly illegal hate speech for which you can get sued and fined and even imprisoned in the EU. But that is actually a very small part, right? And then we have this gray area, and somewhere here are these rules of the platforms, right? They are house rules, let's say. We say, oh, we don't like, we want to have a nice platform, positive people, positive discussions. And some of that might still pass. And this is constantly, of course, shifting in the case of X, Twitter. And if we show some of that stuff that we find or that we identify in HASOC, actually 90%, a lawyer would say, what are you talking about? That's not hate speech. You will never get a judge to sue somebody for that. It has to be, at least in European law, incitement to real violence, very clear against the person, that you can sue. But still, we would like to block a lot of that, and also platforms agree that at least some of that should be blocked. Yeah, here is a definition. We don't have, let's not read it, but it's there. It's of an institution in Europe that says any denigration, as they put it, hatred or vilification of a certain group, insults, negative stereotypes. That's negative stereotypes. That's what we see a lot. That's a very most stigmatization threats to groups of people based on features that they cannot change, like race, color, language, religion, beliefs, nationality, ethnic origin, and it goes on. These are the typically victimized groups here. And especially the public incitement to violence or hatred is something that should be, that is really problematic and that you can go to court against. Okay. These are the typical vulnerable groups, immigrants, ethnic groups. We see a lot of misogynist, also body shaming issues, and sexual orientation, or religious groups, and also sometimes political opponents. Also, we have seen this now in recent elections, I guess. Consequences, is it a problem or not? Because well, I don't see a problem if somebody can say that. You don't have to like it, but why shouldn't they put this online? Yeah, but sometimes for people, if you're really a victim, also some people might not care. But there are, of course, people who really suffer from this, who have a mental strain. Even bystanders sometimes get psychological problems, or they drop out of discussions and are not active online anymore, and their opinion is silenced. And polarization is something that we still see. Maybe it's this happening or not. I think signs are not really yet clear, but could be that we move towards more polarized discussions due to online fora and less reliance on classic media. Yeah, also there is an effect on content moderation. The people who are paid to remove stuff, it doesn't all work with AI. No, there has to be also a human intervention. This is just a quote from one of these papers that report how are they feeling that they have to read hate speech and problematic material all day, and that can also lead to a lot of consequences. There have been reports, and unfortunately, it's also typically outsourced to low-income countries where these psychological problems occur then. So a strange form of colonial attitudes here. The problematic content is shifted to other countries. Okay. Linguistically, what are typical forms of hate speech that we find in our collections that we work. A lot of is dehumanization, right? To call the enemy as some sort of animal or insect, and that is already enough. Okay, then it's no problem to kill him and no problem to harm him and so on. He's not human, he's not like us, so something of a lower category. Profanity, slurs. Also, I will talk a little bit one slide about linguistic creativity as is intensivation strategies, for example, only capital letters or some emojis or exclamation marks that you will sometimes see when people want to be very emotional or negatively emotional or hateful. And of course, also visual content, right? Starts with emojis, but now we should also still more and more consider memes and combinations of text and image if we want to work in this domain. Now, here are some of the dehumanization issues, also animals or robots or garbage, right? These are typical metaphors that are used to detract the human nature of people that you want to put down and hurt and so on. And as I said, now this can be used to legitimize violence. Parasite, subhuman trash, typical with femoid, that also gives this robotic image, machine image, not a human, it's some other entity. Okay, there are questions, not just asking between. Creativity, we see a lot, also a lot in form of hashtags. These are crimigrants, for example, a combination of crime and immigrants, insinuating that immigrants have a higher rate of being criminal and things like that, or some other groups. COVIDiots is this form of idiots and COVID, people who have some sort of attitude that I don't like towards the pandemic. We've seen a lot of hate speech during the pandemics, actually some data sets just on hate speech during the pandemic. And refutards, okay, feminazis, to tell somebody, this is a feminist attitude that is going towards extremism and so on, to promote your agenda of male supremacy or whatever. Feminism is cancer, also a popular hashtag, and white lives matter. Of course we see that. Refugees. These are also some of the creative aspects here. And of course we will see when these things start, the pure lexical method would yet not pick it up and not work yet. So we need this newer method set. Non-verbal aspects, memes, we have very different types of memes. Here we see again dehumanization. We see also memes have also very different levels. We generally say meme, but some people would call a meme only something that we already have seen that is very popular. These images where you constantly change the text and it reappears again and again. When I say meme, we typically would say anything that is visually and has a visual and textual content, and where they often work together. Sometimes there are, not in this case, but there are just images that are illustrated. The text alone is enough. There is already a hateful message, and the image just is there to make it more popular and so on. Okay. And it has also been observed that especially visual elements try to make, and memes try to bring hate in a more or less funny way, that people say, oh, it's a joke, I can laugh about it. But actually behind that, there is this whatever strategy. And that is often, so this kind of humor is often used to promote a agenda, and especially has been observed that in the extreme right movement, extreme far right movements, these strategies of using humor and visual elements are very, very popular and widespread. So they seem to work well. Yeah, interestingly, there was a nice study by Java at the Human Computer Interaction Conference. So I was quite surprised. They looked at some fora and identified the people who posted hateful messages and found a few of them and interviewed them, and also interviewed victims. Quite interesting. And they, of course, have completely different opinion of what is going on online, right? The haters often say, we protest, we can say something that should be allowed in a democracy. We claim freedom of expression for us, ourselves, no? And people shouldn't be so sensitive. Whereas on the other hand, so they don't see this as hate at all, oppression by some social left elites or something like that. This is censorship, shouldn't be done. Whereas the same study, it's not on the slides, but they also interviewed the victims and they said, yeah, they dropped out or couldn't sleep. So they were really affected also, or some of the victims were really affected. So we see a very diverse perspectives on this now, on the same thing that is happening. Yeah, so that's also quite interesting to see how does that fit in. If we say hate speech, people who post it might say, what are you talking about? Nothing that you should worry about. How can we react and what should be done? Ignore, of course, is a very common approach, I would say. Report. Many platforms have report buttons. In 2017 in Germany, that became mandatory to have that and to quickly react to these reports. And they also had to be very, very well visible. Directly on the post, you had to have a report button then. Report to the authorities in case you think this is really illegal, make a screenshot or whatever, download and report and sue the person. Happens probably very, very little. Counter speech is also a method. There are also projects and even data sets of effective counter speech and what can you do, what is effective, how can you run that. Also automatic methods, of course, nowadays. And of course, AI, the methods that we use, automatic detection. And what happens then? That's also the next question, of course. Then again, you can go through all of these options and we'll see a bit more in detail later. Interestingly, it's also a nice quote by Mark Zuckerberg. He said, yeah, Facebook say it's difficult balancing act to weigh what is acceptable and not. Yeah, of course, but if you make so much money, you should be able to do also a difficult job, right? Much better than you're doing it right now. So just hire a few more people. And another problem is that some reports say that especially hateful and objectionable content is amplified, right? So it gets a push through the algorithms. People look at more at it, engage more with it, maybe or find it strange or maybe even funny, and that is even has a higher impact. So that's probably, we would say, the worst that should happen. We would prefer some of these actions, but no, actually, what happens around it gets amplified and even promoted more. Research is also there, not just HASOC is doing this stuff. Here is a plot from 2015 to 21 on what are the problematic contents where research papers were published on, right? Child pornography, human trafficking, sexual abuse, and so on, typical political propaganda, violence. And we see, hate speech is almost on top of that, right? Misinformation is now very popular, and illegal content, probably fingerprinting stuff for copyright violations and stuff is above. But we see that there is a huge increase also since we did FIRE. Some of these are our papers, of course. We also pushed a little bit for the Indian community thanks to the help of so many people. So there is research going on, happens. Huh? Of course, this is just a slide to say, yes, we should not rely on lexical methods. Even a Nobel laureate winner of literature says, be careful with words. And we in AI, we would translate this. Don't use lexical methods, use transformers and some deep learning methods, distributed representations. And yeah, with that, we see, okay, now we're at AI. What happens? What are we doing in classification? A simple perspective from the beginning, also difficult enough, of course. So a brief look back at HASOC, just 2 or 3 minutes. We are running the shared task now for a few years, 6 years actually. We have our definitions, hateful, non-hateful. There are some schemas that are more elaborate. The one that we used for Bengali this year, the OLIT, that also has a second level classification on what is the target. This is the group, individual, and so on. No, I'm a bit skeptical. It increases the time and cost, of course, for annotation. And is it really that relevant? No, I would prefer something, annotation where if we had time and money on what is explicit, what is implicit hate speech. I think that would be linguistically and computationally interesting. So we went with this definition for the whole time. We produced quite a lot of output. We had 12 languages, many English languages. We got data collections for lots of papers that we published in the SOIL proceedings. And once I checked on Google Scholar, the crawler stopped at around 700 mentions of HASOC when you search just for HASOC there. So there's also an impact outside of this community and also this closer SOIL proceedings. It's also used in other stuff, so that's also very good. Yeah, then we get typical results or typical data sets, sizes. This is just an example from 21, I think. A few thousand, few hundred data points that we can develop. And we see some results. Here's 2020. We still have BioLSTM and not BERT yet there. So we went through all the development of transformers.
Yes.
Oh. Okay. Okay. Somebody gave food there. Yeah, okay. No problem. And these are, I'll just continue. These are the Indian language data sets that we managed. And now the question is, of course, what kind of biases might be there? What kind of biases might we have? But also other data set collections. It starts already with the collection of platforms. Sometimes we use an API, right? In Twitter and this stuff, it changes all the time, but often we have an API access. And we fully depend on the platform. We have no idea, does the API give me the same results as the user sees? Or is it a completely different set? We simply don't know. There have been some experiments recently at the workshop that we organized. And they said, well, which platform did they look at? Was it Twitter? No, it was TikTok. And they said, well, API results, we cannot predict. We have no idea what comes back. And quantity, time level, there is a time delay, and all of kind of biases are already implanted in the API. So it's very hard to say, is it representative of anything? Sometimes we also call timelines of users, right? People who sometimes put hate, but sometimes it maybe talk about soccer and stuff. Then it's also a bit problematic because then we focus maybe too much on individuals, single individuals. And let's stop here. We go on to our biases. So this technical bias. Then, of course, we search in our API with some words that we think, oh, what could happen? What is a good topic to find hateful speech? No? And of course, we have some good knowledge of the situation in the society, but we might not know everything. There might be a lot of topics that we don't think of, right? And there could be some also smaller collections of smaller topics of hate that we don't cover. And then we have no idea how good our AI will cover them. So this technical bias, knowledge bias. Then there is interesting, of course, the quantity bias. In some publications, they estimate that around 1% or less of text posted in social media are hateful. We never have a data collection where 1% of the texts are hateful, right? We intentionally, to give the AI a chance to do something well, we oversample there when we do this. So our tasks are different from what the platform has to do in a daily basis, if they do their job well, or if they do anything. So this quantity bias also problematic. If we give a 10 to 90% data set or 80-20, sometimes we did more or less that, all the participants will complain in their participation papers, oh, the data is unbalanced, we cannot work well. No. Well, we are already oversampling, you know. This is the problem. That's what we have to solve. We shouldn't complain about how the world is, right? We have to solve it. So these are just 3 of the biases that appear there. And that we have not really good tools and not really good methods to measure them or to track them. This is, I said, from 1 or 2 publications. We don't know the real distribution of hate speech. Is 1% or less. It's just an estimate. When we give this to annotators, then we have, again, lots of biases. Humans work with some data. Lack of context, that's a very typical one. Yeah, we had one task for that. Quotations, that's also an interesting thing. People quote something, put it in quotation marks and say, somebody else said this hateful stuff. No? But if you identify, if you don't say anything against it and redistribute it, it's actually not a quotation, right? It should be also labeled as hate speech. And a graphic material, sometimes we had posts where we say, oh, obviously there used to be an image there, but we didn't call it in our early times. We just give text. And then what can we do with that? Then, of course, the rating also can be quite different. We have different knowledge levels. I have a PhD student now who works a lot of on anti-Semitism, and she says she has to really train their annotators well to know typical stereotypes and typical problems of anti-Semitism, to know the signals that are used, right, about to insinuate images of the Holocaust and so on. They are not obvious for anybody. And so after training, the rate goes up tremendously of the positive or negative or hateful things. And probably it's a huge difference whether the annotator is a group of is a member of such a group. We don't control for that, right? I don't know if we publish gender of our annotators. Probably not. No, nobody does that. Probably it's different if you see a misogynist tweet, if you're male or female. And of course, knowledge level can be influenced by age and many other things, familiarity with social media and so on. Of course, different tolerance levels. You would say, yeah, this is gray area or not. No, how do you rate it? And even if we discuss things sometimes we discuss questionable tasks, but for most tweets, the annotator is alone. And typically we don't have money to pay 2 or 3 or 5 annotators. Some people have done this. What was her name from Italy? They did an annotation of 10 people per tweet, and then they tried to predict the probability distribution. That's of course very interesting, but very expensive. We cannot always. And of course, we have to be aware that the students' speed of annotation, sometimes they just want to get done with some task at the end of the annotation, end of the day, dinner is calling, right? And then they might go more quickly than in the beginning. So lots of these biases are there. And also there's has been shown in IR also the quantity bias, right? If I have already encountered a lot of hateful tweets, I will be more relaxed. If I have encountered very little of what I'm looking for, I will take everything, right? Everything is close to relevant, or in this case, to being close to being hateful. Oh, and probably the list goes on. So we see there is really a bunch of issues there. Here we have also demographic distinct annotator groups. This also bias is introduced by first language age education, at least these colleagues from TU Munich, they published on this. Yeah, also the topics that we encounter, that's also quite interesting. Often we don't even look at what is in the data. And this time I looked, I automatically translated the Bengali set, or is this the English set? No, Bengali set, and checked. And of course, I'm not so familiar with the things. This is just I think it's just the hateful tweets that I analyzed in a BERT topic modeling. And you see, okay, Muslim Bangladesh, India, yeah, probably there's a lot of hate speech in the area, in the national issues, politics. And then the topics get much smaller. Nah? Probably you have a much better idea whether this is, makes any sense or not. And these are, again, the topics for the test set. Now we can see, oh, is the test set different from the training set? Are we expecting something from the model that we cannot deliver, that it cannot deliver in the test set because maybe we give it completely different things? But again, we see Bangladesh Muslims, some gender issues maybe, and for these, of course, this topic model is also not a very hard scientific analysis. I also did a plot in a TSNE plot, put it in a two-dimensional space to see how well do the two sets separate, right? Hate and non-hate. This is one is hate and one color is hate, one is not hate. And if they would be completely separate, we would say probably it's a very simple topic analysis that the algorithm actually does, right? It's Bangladesh, then it's about hate, or it's Muslim, it's about hate, and it doesn't really look at the content itself. But yeah, they seem to mix, at least in this TSNE plot, and that would be a positive sign, I would say. Yeah, current topics in hate speech detection. Now we have lots of data sets. There's more and more analysis on cross performance, right? Does it only work for this data set that we trained for, or can it be used in reality? Continual efforts, continual training, and realistic scenarios. And we see that this is a analysis that one of our students did for the 8 or 7 German hate speech class sets that we found. And we see the cross, we have a good performance, and then it drops sometimes drastically. Here it drops more. For this data set, it drops a bit less. And then we go to levels probably that could not be used in real life. Right, F measure, and that's of course quite worrisome also. And we don't know why it drops more here and less there. We don't have really good measures to see what is the quality of, or what is the comparability of these data sets. They're all, of course, collected in different years and so on, different topics. We see one is only on COVID, and of course our HAZOCs are also there. Nah? So that's, I think more research should go into these dataset analysis. Now the student also mapped the things in a TSNE space. What is the not category for each and what is the hate category for each of the data sets? And it would be, of course, good if hate and non-hate are close together and if they're not separated already by the topic, by the topic model, that would be perfect. And we see some are closer, some are far away. We also had a look recently at the details of the classification. So what is the distribution of the classifiers? Is there some agglomeration of the results? And where is the F1 measure? Here we did a work with the director here, Bandyopadhyay, with the Bandyopadhyay. And we also looked at how well do all these classifiers that took part in one particular HAZOC solve the tweets. Which tweets are solved by most of them? We call them easy. Which are solved by none of them or very few, that we could call difficult tweets, right? Difficult tasks. And how does that distribute? And surprisingly, we find that if we split that into 20% buckets, we get the result that most tweets seem to be rather easy. They could be identified by almost any technology that you implement, by either the worst system, right? And some seem to be very, very difficult. That's what we see in this empirical result. Then we took a look at, well, is it really the case that these easy ones are solved well by the simple methods, right? And the other ones are solved only by the very elaborate, very good systems. And actually, it's not the case, right? It's actually opposite. Here we have our 5 clusters, simple ones, very difficult ones. And here we have the top ranking systems. Here we have the lowest ranking systems. And we see in the difficult class, we have a surprisingly low performance of the top themes. And we have they perform excellent on the easy task. Huh? And there are many, so they get to the top, but the ones that are difficult, that are hard to solve, are actually better solved by the, much better by the worst performing teams. There could be some randomization effect, random effect, but still we have, because they are difficult, you could just guess, but not sure. And they perform not so well on especially the very easy ones. So this is interesting, probably we should look more into that. But there are a lot of things, I think this is just one example, that we can still learn from all these tracks and all the shared tasks that we have run. Get the results, have a detailed look, and try to analyze patterns, find patterns that are interesting and report them. This could also maybe help us in the future to develop better data sets and other ideas. Yeah, with also the problem of context. I think it's very relevant, and also seemed to call a lot of attention. Our work, 2 years or 3 years, we ran a contextual task thanks to Shrey. And we would say a tweet like "Happy birthday" seems to be positive, but it could be hate speech if before people talked about the anniversary of the assassination of Gandhi, for example, right? And you would promote his agenda, and then we should also say, "Oh, hey, happy birthday! No, that's hateful. We should do something about it." And we created this data set where we give not just one tweet, but also the previous history of at least 10 tweets, and the models could use that as they would like to, right? How much influence do you give to the top tweets to use it? Do you just use the previous one, or what do you want to do? Yeah, unfortunately, interest was a little much less, so but this data is still there, and people could still run interesting systems there. Explainability, there's a lot of talk about explainability and say, oh, we use some of these Lime or Sharpley to give a rank to the words, right? And then we have words and their distributions. I don't know if this is a good explanation and helps. We are moving back to the lexical level now, and does it really help me? Depends a lot on the application, but I think in most application, Lime and Sharpley should not be the end of research. They seem to be rather simple methods. Visual content, of course, we also participated in one shared task for English in a few years back. And what we observed there is that the strongest predictor, if we just run single channel detectors, is still text. Text outperforms, and it's just sentiment images by a big margin. Text is still the dense, most rich presentation that is easier to analyze than images. But we have to look at that too. Counter speech, there also have been projects, one in our university, where people said, how can we react? And people created a dashboard and a system where an activist could get a prepared meme, prepared visual content to react to some hate speech. And people were trained in using these systems to stand up and not be just a bystander, but to react against hate speech. Okay. Yeah, ethical frameworks. There's of course also discussion, should we censor or not? all the reactions that are possible. Quarantining, cooldown phase, downranking is also very important probably, but we can also expect just block accounts, censorship, or what are reasons to limit censorship is from the Indian constitution. It's also a good example for what can be blocked and what should be blocked and what not. And why should we not block as much as possible? The German philosopher Habermas, he declared democracy can only work if we have a positive discussion, right? What he calls the ideal communication situation, free media, we can discuss everything, and then we should be rational enough to select the best solution, even if we have a different opinion. Obviously, that's not always happening in social media. No? And this is called the discourse ethics, right? Best arguments, if it's presented in a rational discourse, then we are able to identify it and select it. If we just have hate speech, it's not good. But if we censor the part of these rational ideas, of these good ideas, then we are not doing a favor to democracy and progress. Good ideas should be heard. Regulation, US, Germany passed a law, but it's pretty much was a blueprint for the, let's go to the DSA, for the DSA that passed in 2022, Digital Service Act, quite influential, and that says, yes, we can censor, we have free speech, but we can also censor, and we govern the content moderation practices of social media. We tell them what to do. They are liable, right? Not as in the US, I think maybe it changed now, but the US says, okay, this is just a platform, people who are active on the platform, they are responsible. And the EU says, wait a minute, platform makes a lot of money. They also are responsible, right? They're doing something. They should pay fines and be responsible, and we tell them what to do. And that's good. Different from the privacy regulations a few years earlier, that PSA made a difference between maturity levels. So only very large online platforms have the highest responsibility level. So there is no punishment for a newcomer or anything, right? You still can get into the market. For privacy, that's only difficult. And this is around 18-20 platforms, so only the big players. For example, one of them, Reddit, I think, was not in the list when the law was passed, but meanwhile they developed, now they also VLOP, and they have to follow the strictest rules. 45 million users, and then you have to disclose to regulators your algorithm. How do you work? Do you amplify bad stuff by intention or not? How do your algorithms work for hate speech detection? Are they really good? Are they not over-blocking? Are they not under-blocking? So the regulators have a chance. I know really exactly what they look at, and it's still difficult to define that, but at least the door is opened, right? And there have to be transparency reports. If you're notified, that's the core, no? You can notify the platform, wait a minute, there is hate speech, and then they have to react. They can say, no, that's not hate speech. And then you can have a decision, you can go to court, you can object, but they have to do something. Or they can say, yes, it is, I will block it. Then the person who is blocked can go to court maybe, no? But still they have to react. And especially, for example, for the trusted flaggers, if a social society organization comes, they have to react quicker because we say, oh, they're really experts. So that's also very good. Unfortunately, the financial situations of these trusted flaggers is not talked about in the DSA, but yeah, it's as good as it gets. And we still have problems. Twitter problem of there was a voluntary pact on fighting disinformation agreement in the community, but we shouldn't trust these voluntary commitments. And it does not attack only hate speech, but also disinformation, cyber hate, and other problematic content. Of course, there's also very recently now the AI Act that might also affect that says we have high different risk levels, unacceptable risk, for example, face identification in public spaces, and high risk that would be medical applications, and down the line. And LLMs, foundational models, they have a special place, right? Foundational models also should fulfill some of the obligations, but they are not within these risk categories. The Indian situation I'm not so familiar with, no, but you might know better. For time reasons, we move on, I guess. And just a very last issue on a look at these effects of regulations, right? We have now also this, as I mentioned, the transparency, transparency platform where all the platforms, whenever they do something, whenever they get notified, they have to add a line into a public database. You can access it, download it, and work with it. And they do that differently well. No? Twitter always puts the same reason. No? So they are just lying to us also in this transparency database. They should just be fined just for that. And other platforms say, yeah, 20% of the cases were like this. Some of them were followed. Some of them we didn't follow. So we can see what is happening. People have analyzed this, but people have also done other stuff. We say, you don't do enough. But what happens if you react, right? This paper reports on 11,000 YouTube channels of the far right. They were deplatformed. And what happens? They said, yes, most of them had a good effect. Extreme speech was removed. And people moved to alternative platforms, some of these fringe platforms, and they are not so able to reach people, and their effect was going down. So regulation is positive. But there's also this paper from this year that says changes nothing. It makes the things worse. They analyzed a ban in Reddit 2020. Obviously, no, 2,000 subreddits were shut down. And this paper observed what happened to the players that were active on these 2,000 boards. And they said there are many left platforms, working cringe platforms, and we look at their subsequent posts before and after the ban. And some decreased, the mean toxicity decreased, but 5% of these players even increased their toxicity, measured by automatic methods. Now we always, of course, some margin of error, but they would say, actually, we always say, tell the platforms, please block, please do something. But if they do it, things don't change really. So I think this is also a very important field for research. What are the effects of all of these measures, counter speech, blocking, downloading, and so on and so on? Are they helpful? And how do we define helpful? Now, what is our actual goal? Yeah, so with this negative outlook, I thank you very much for your attention.
Thank you, Professor Mandal, for your talk. I'm pretty sure like it will motivate at least some of the researchers to start working on hate speech now. I think due to time limit, we can probably take 1 or 2 questions now, and then you can discuss more with them offline. Yeah, any questions? Well, if not, I have one question. So, I mean, whenever we say that I work on hate speech detection, the first question we encounter is like, how do you define hate? Because there is a lot of subjectivity involved. So I think nowadays there is a lot of work going on in personalization, in information retrieval, summarization, etc. So do you think like personalized hate speech detection model, like, I mean, at least it can moderate content for your field. So do you think that can be a potential direction to look for?
Could be interesting research perspective. Now, of course, from a regulation perspective, would make things much more complicated. Is it illegal? Is it just illegal for you and not nice for you? But that could be for example, a setting in the social media platforms. Or I don't want any hate speech. I want some hate speech. No? Or I'm more flexible. Or I really want to have positive content and stuff. Could be an option. Then we would again have to check the effects. Good
Thanks a
idea.
lot. Yeah, any other questions?
Hello, good morning. So, as you mentioned that there is kind of a gray area between the illegal speeches and what people call freedom of expression. So what are your views on how can AI differentiate between, and how can AI basically reduce that gray area in the middle to have better results? Can you please
elaborate on that?
Good question. In the ideal world, we would have a continuum, right? That's already hard to define, and AI would just label it where the post belongs, and then we could say, oh, here is a cutoff, or this is illegal, this is against the house rules, and this should be still acceptable, and we could fine-tune that. But I don't think it's really a continuum. It's very hard to define these borders very well. So I would be rather skeptical. We are already battling with identification. We've seen F1 measures of around 0.8, and also identifying this gray area clearer and differentiating it from real illegal hate speech. I think it's very hard, but maybe a good topic.
Can probably take one more question if you have. Yeah. Otherwise, I think now, yeah. Thanks a lot.
Sure. Thank you. Thank you.
I think now we'll move to the next track presentations, chaired by Sharon.
So thank you. So we are going to have a presentation on word level language identification in Dravidian languages. So we have 6 participants and 3 online presentation and 3 offline presentation. So we'll start with the first presentation, that is by Aniket. Okay. Can you call Aniket? Oh, okay. He's here. So the paper title.
Thank you. So I will present prompt engineering using GPT or word level code mix language identification in low resource Dravidian languages by Aniket and Subankar. So let's start. So the introduction. So the task was a 6-class classification problem in Dravidian languages. It was a word level classification problem. So there were different categories of words like mixed words, words in different Dravidian languages, words in English, names, locations, etc. And we had to perform a classification task. So this was the data sets that were given to us. There were 4 data sets. The Tulu data set was 7171 code mixed sentences sourced from YouTube videos. These sentences had undergone pre-processing to eliminate non-textual characters and have been translated into Romance scripts. And there were 6 classes: Tulu, Kannada, English, mixed language, name, and location. Then there was the Kannada dataset, which was around 14,847 tokens in Romance script. It was categorized into 6 classes: Kannada, English, mixed language, name, location, and others. Next, there was a Tamil dataset. It had 17,568 tokens, following the similar methodology to Tulu and Kannada datasets, and also had 6 categories. And then there was a Malayalam dataset. It had 25,000 tokens, classified into 7 categories: Malayalam, English, mixed, name, number, location, and symbols. Now the task definition: the words should be classified into 6 categories: English, which are phrases or words in English language. Then there was Dravidian words. There were mixed language words, which were mixed in English and Dravidian languages. Then there were names, proper nouns, including names of people, organizations. Then there were locations, locational information. Then there were symbols like star, and then there were other categories. So we used a GPT 3.5 turbo-based approach. So via prompting, and the reasons are shortly discussed. First reason is code mixing in text. Next is the accuracy in language processing. And the next is the contextual understanding capabilities of GPT.
Next is the challenges and innovation. Next is the prompt engineering based approach that we used. So we used the following prompt for Kannada. We participated in two tasks, Kannada language and Tamil language. And we used the prompt for the Kannada language. Please identify which category the word is in: English, Kannada, mixed, name, location, symbol, and others. And then we asked, please state EN, KN, mixed, name, location, symbol, and other. So these were the 7 classes. And then we gave the word. Similarly, we used a similar prompt for Tamil language. Please identify which category the word is in: English, Tamil, mixed, name, location, symbol, and other. Please state EN, TM, TMN, name, location, symbol, and other. So we used 2 simple prompts for classification. These are the results. So we saw that the results for Kannada language were a bit better than for the Tamil language. And we also observed that the weighted scores were better than the macro scores because there was class imbalance. The classes which were present in higher amounts, they performed better via our classification methodology. So the weighted scores are a bit higher than the macro scores. So the final conclusion, the methodology employed in this research leveraged GPT 3.5 Turbo via prompting, harnessing its NLP capabilities in code mix text. We saw that there is a large scope from improvement because we need to improve the prompts, and maybe we try few short techniques or fine tuning the models to better improve the capabilities. The capabilities currently for GPT 3.5 Turbo for Dravidian languages is quite mediocre, I would say. So it needs to be improved quite a lot via improving the techniques. Thank you.
Thank you. Any questions? Okay, just I wanted to know, like, why did you use only 2 languages? Didn't you try other 2 languages? Like,
Probably time constraints.
okay, fine. Thank you. So, thanks. So next we have Kavya ji from Mangalore University. So, her paper title is Enhancing Word Level Language Identification in Code Mixed Dravidian Languages.
Good morning to all. My name is Kavya Ji and I am from Bangalore University. So our paper title, it is Enhancing Word Level Language Identification in Code Mixed Dravidian Languages. So the authors of these papers are Sonit B, Kavya Ji, Asha Hegde, and H.L. Shashireka. So the task is like word level language identification in Dravidian languages, that is Kannada, Tulu, Tamil, and Malayalam. So for this, we have proposed use 2 of the approaches, that is sequence labeling approach and sequence to sequence labeling approach. So under the sequence labeling approach, we have proposed 2 of the model, that is COLI-CNN and COLI-TNN. And for the sequence to sequence learning approach, we have used BiLSTM encoder and LSTM decoders. So to concentrate about the methodology, first we have pre-processed the data, that is like whatever the numerical values were there, which are converted into their textual forms. And the proposed models for sequence labeling, that is COLI-CNN. In that, the CNN classifier, which are trained using the neural embeddings. So next, it is the architecture of the COLI-CNN model can be seen in the figure 1. And the second model, it is a COLI-TNN. It is a transformer neural network, which is on a self-attention mechanism. The hyperparameter which are used in the COLI-TNN, which can be seen in the table 3. And the next one we have used is a sequence to sequence approach by using the BiLSTM encoder and LSTM decoders. The framework can also be seen in the figure 2. And also the hyperparameter which is used for training the model can be seen in the table 4. Next, in the experiment and result, the statistics of the label distribution, which can be seen in the table 5 for all the languages, that is Malayalam, Kannada, Tamil, and Tulu. So among the proposed model that are like COLI-CNN, COLI-TNN, and sequence to sequence, The performance of the proposed models can, for the validation set as well as the test set, can be seen in the table 6 as well as 7. So when we have observed that proposed models, whatever the proposed models we have, among that, Kohli CNN has outperformed all other models for all the languages, that is for Kannada, Tamil, Tulu, and Malayalam. It has secured macro FN score of 0.8028, 8400, 0.6994, and 0.7854 for Malayalam, Kannada, Tamil, and Tulu, securing the 6th rank for all the languages. So as a future work, we will be dealing with handling the data imbalance as well as certain combination of features. Thank you.
Okay, question from all. Any question? Okay, did you try ML models? Like, have you tried?
We have tried all the models, ML models also we have tried, but most of the times ML models has been worked. So we wanted to try some new concepts. So we have tried with the different
So
models.
what kind of features you have used in ML models?
ML models, we have used TF-IDF.
Thank you. So the next presentation is by myself only. I'm going to present the like a paper named Word Level Language Identification in Code Mix Dravidian Languages. So already other participants explained about introduction and data set. So I'll just start with the methodology part. So our team name is MUCS NLP. Okay. So introduction, yeah, because we are going to identify the languages. So like here they have we have used four languages: Kannada, Tulu, Malayalam, and Tamil. So the main task is to identify whether the given to identify the languages. So here we got this is the data distribution of train and test set, which we got, a validation set, which we got. And like in this work, what we have done, it is a sequence labeling task. So we have used the CRF model here, and we have used the CRF suite using that library. And so what we have done, we have taken some textual features here in our work. So this is how it works. Like we have taken the train and test set, and we have prepared the data for our CRF model, and we worked on it. And so these are the features which we used in our work. We used word, length of the word, and previous words, and previous to second word, previous third word, and next word. And this is the example which we have taken, like Tulu example we have taken, and as well as Kannada example we have taken here. So why we have used means like to capture the dependencies and the relationship between the words in the given sequence. So these are what we have done. We like proposed 3 models. Like we have submitted 3 runs. So here in the first run, what we have used in like just we changed the parameters over here. We changed the optimizers as well as C1, C2, and like iterations we have considered 200 only. So these are the results which we got. For validation set, what result we got? No, so like that is for run 3 we got. For Malayalam we got better result for run 3, and for Kannada, Malayalam, and Tulu we got for run 1 we got a better result. And like conclusion, I could say, like started with one language, and like we thought we can improve in other 3 languages. So we sent our we sent all the predictions to the shared task, and our like we started with ML. SVM DT, we used TF-IDF and all. Then we thought we'll work on CRF model, so we sent that predictions only. So next we want to, the data set which whatever given was imbalanced. So we thought, I mean, in the next edition, we will try to handle the data. We'll try to balance it and we will work on it. So thank you. So any question? Yes. No? Okay. Thank you. So we have 3 online participants. So Rob, are you there?
Yes, good morning.
Hi, good morning. So you're ready, right? Ready with the presentation?
Yeah.
Yes, you can share your screen.
Okay.
And I think you can start with the methodology if you are fine with that.
Yes.
Thank you.
Okay. Thanks. So I'm Rob van der Goot and I represent Team NLP North. Today I would skip the intro on the data. I just talk about the methods. And I have 2 final points I want to make afterwards. So what did I use for this task? As a starting point, I used the MatchAmp toolkit, which is a toolkit based on Hugging Face. You can very easily extend the Hugging Face models to perform downstream tasks with this toolkit. I mapped all the labels to a uniform set so that I could also do cross-data set experiments. And I evaluated 37 different language models based on the languages they included. So either they included one of the target languages or they were highly multilingual. To improve performance, I tried adding a CRF layer. So not the CRF classifier as the previous people, but the CRF constraint layer that uses that scores transfers between different labels to see if this contextualized information can help. I did multi-data set training, so this is possible because I mapped the labels to a uniform set. And I tried to add a language modeling objective, so doing mass language modeling on the target data and see if that improves performance. So all the detailed results are in the paper for all languages, for all setups. But to give you the quick takeaways, the CRF helped in some cases. It didn't help in other cases. For multi-data set, it was exactly the same thing, and also for language modeling. So there were very mixed results. There was no stable conclusion on which of these techniques to use. So why did I get such high scores then? One might ask, because I ranked relatively high. And the real only secret is that I tested on 37 language models. Without that, I would have not get a good ranking. So this, of course, leads to the question then, which of these 37 language models should we use? And how can we next time predict this beforehand so that we don't have to lose all this compute? So to get an answer to that question, I calculated the Pearson correlation of performance of language models to different variables. And here you see the 5 different variables that I came up with. And in general, the scores are not super high. So it means it's quite hard to predict which language models to use. And there are also some strange trends in here, like vocabulary size doesn't really seem to matter. The number of languages also, like more languages is better, it seems like here. But this should all be taken with a grain of salt because there's many confounding factors here. All of the large language models, for example, are multilingual. So that means that if you have more languages, you also have a larger model automatically, and that might be the reason for the higher performance. So we should be careful to use these directly to make a decision. Then I was quite curious which errors still remain. So I did some qualitative analysis and some quantitative analysis. This is the quantitative part that I show here. So here on the y-axis, we have the labels, the map labels, so the uniform labels over all data sets, the gold. And on the x-axis, we have the prediction of my best model. And as you can see, there are quite some categories that never get errors, and there are some trends of categories where we have more commonly errors. Canada and Tulu are more often confused because they actually occur in the same data set, whereas the other languages are only code switch with English. And the errors for this categories are mainly for words that are ambiguous. So these are words that exist in both languages. There's an underprediction of the miscellaneous category, which makes sense because miscellaneous is probably the least well-defined category because there's a variety of stuff in there. And for the mixed languages, we see the mixed labels. We see that they are hard to predict, and this is because upon manual inspection, I saw that only the inflections are done in English. So the English part is really only around 2 characters of length usually, so that's hard to identify for the models. Then the English label has quite some errors. This is because interjections are hard to predict. So you see some examples on the slide, but also there's typos in slang that are often predicted as other languages. So for example, the word da, which was predicted as Tulu. And I found some annotation inconsistencies where I wasn't sure whether this was an English word. So there's 2 examples on the slides. Okay, so finally, I would like to thank the organizers for creating the data and setting up the shared task, and also our own HPC, because I needed some compute and they provided it for me. So, thanks.
Thank you. So any questions? Okay. So thank you. So we'll move on to next presentation. Thank you, Rob. Okay, I
Thanks.
think you can stop sharing. Okay, fine. So next we have Abdullah Abadian. Are you there?
Yes, I'm here.
Okay. Okay, hi. So I think you can present your screen. I mean, you can present now. You can share your screen. Yes.
Okay. Hello, everyone, and welcome to my presentation. On language identification in Kannada English code mixed text. Today, I will be discussing on our study finding and implication, focusing on the challenges of identifying code mixed language in social media context. To begin with, our objective was to explore the challenges presented by code mixed languages, especially looking at Kannada and English interaction within YouTube comments. We aim to shed light on the complexities of language mixing and its implication for natural language processing. In our study, we utilize several machine learning models for language identification, including Navi Bayes, Support Vector Machine, and Decision Tree. We assessed the performance of these models using K-evolution metrics such as F1 score, precision, and recall, which help to measure the accuracy of our language classifiers. K findings. Our results were quite revealing. The support vector machine models significantly outperformed the other classifiers, achieving an impressive F1 score of 81.2% in comparison. Navi Bayes had a score of 72.5%, which was limited due to its assumption of independence among features. Will the decision tree perform moderately, coming in at 75.3%. Context and language complexity. One interesting finding from our research was the impact of comment length on language identification success. Longer comments tended to contain richer linguistic cues, which aids our models in making more accurate predictions. Conversely, shorter comments often result in higher rates of misclassification due to a lack of contextual information. Looking forward, our study suggests a few permission avenues for future research. We recommend the exploration of hybrid models that combine the strengths of various classifiers to enhance performance. Additionally, we see potential in applying advanced techniques such as neural networks, which include improved language identification in multilingual contexts. In conclusion, our finding emphasized the significance of tailored approaches like SVM and language identification tasks. However, there remains much to explore in this field. Future research should focus on utilize larger and more diverse datasets, as well as investigation our multilingual setting to deepen our understanding of code mixing. The implications of our research extend beyond academic interest. Understanding code mixing is essential for developing accurate language processing tools, particularly in today's globalized world. Our finding can support practical application, including social media analytics, language translation, and real-time communication for bilingual speakers. Here are some key references from our study, notably Hedde and Baluchzehi and Lakashamaya Baluchzehi. Thank you for your attention. I hope you found this presentation insightful. I am now open to any question you may have.
Okay, no, thank you, Abadian. So I have one simple question. Did you try to balance the data because the data set was provided imbalanced, right? So did you, considered, have you tried?
I have from reference Hedde and Baluchzehi data set.
Okay, fine. So you mean like you use that data set without balancing the data, right?
Yes,
Okay, thank you.
thank you.
Thank you. So I think you can stop sharing your screen. So any questions?
Okay.
Okay, fine. So now we have Purna Subhash. Are you there?
Yes, I'm there.
Yes. Okay. Hi. So I think you can share your screen and you can start presenting.
Okay. Hi, this is Pon Subhash. So I will be presenting on my study on the comparative analysis of models and vectorization techniques for the word level language identification in Dravidian code mixed text. So we have already discussed the problem statement. Now I will try to address these problems with computationally efficient ML approaches. So for the methodology, first of all, I've oversampled few of the underrepresented categories in the training dataset, which helped me in improving the F1 scores, macro F1 scores. And then the words are converted to vectors by using the frequency of the occurrence of characters at n-gram levels. So I've used both for the comparison, I've used both TF-IDF and count vectorizers. And then the model is trained using basic machine learning techniques. So for the models and vectorization techniques I used 4 models: logistic regression, support vector machine, decision tree classifier, and a voting classifier, which is an ensemble of all the 3 models. For the vectorizers, I used count vectorizer and TF-IDF. So I'll talking about each of the data set findings. First of all, Tamil. So I've shown all the performance of all the models and vectorizers in table, and then the training data composition after oversampling. And then we find that the best F1 score is for voting classifier with TF-IDF vectorizer, and closely followed by other models as. And then for Kannada dataset, the best performing model was a logistic regression using count vectorizer and a support vector machine using a TF-IDF vectorizer. For the Tulu dataset, the best F1 score was voting classifier using count vectorizer and support vector machine using count vectorizer. For the Malayalam dataset, the highest macro F1 score was in voting classifier using count vectorizer. So for the final findings and insights, I have seen a trend of a voting classifier which stands out as the best model to proceed with for the language identification in code mixed text. which balances both the accuracy and the computational efficiency. For the vectorizer perspective, both TF-IDF and count vectorizer have shown similar overall performance. But if we see more closely, count vectorizer has always outperformed TF-IDF vectorizer in some of the important categories like mixed categories. So the impact on future NLP tasks, this model can serve as a pre-processing step to improve the accuracy of applications like sentiment analysis, named entity recognition, and machine translation in core mixed context. So correctly tagging languages helps models capture linguistic nuances and context in multilingual data. So here are my references, and thank you.
Okay, thank you. So, any questions? Okay, we have one question.
Yeah, so you used a decision tree classifier, right?
Yes.
And also something like ensemble approaches. So
Yes.
why didn't you try the random forest in that? Like your accuracy in decision classifier is pretty good in each and every one, right? So better to combine all the ensemble, like all the classifiers, just to use random forest, and maybe it can get the same output accuracy.
Yeah,
Right?
I also tried a random forest, but it didn't give like as much accuracy in some of the, like I mentioned, important categories like mixed categories. So actually, if we see individually, LR model, a logistic regression model, had the best in like mixed categories. So if we combine all this in a voting classifier, it actually gave better F1 scores overall across languages.
Okay, thank you.
Thank you. And I have one simple question. I think you can try the XGBoost also, I guess.
Yeah,
Yeah,
I
I
thought
think.
about it. Yeah.
Okay. Thank you.
Thank
So, thank you. So
Okay.
I think we can wind up now. So thanks for participating our task, and thank you all. So thanks. That's it. Thank you.
So I guess we have some free time, and in that free time we can accommodate someone's presentation which is shifted today. So Sangeeta, are you present right now?
Are you listening to me?
Yes, you can. You are given a 5 minutes window. You can start your presentation now. Thank you.
Okay. Are you listening to me?
Yes, we can.
Hello?
You are audible. You are audible.
Okay, okay. Yeah, I am Sangeeta Singh. I am here to present for Indian language summarization on topic enhancing extractive summarization for low resource Indian language using TF-IDF and SVD. These are my outlines of my presentation. Let's start with the introduction and following by the literature survey, problem existing solution, motivation, and our proposed framework. Then results, conclusion, references. Here first we text summarization. We extract the key points from the large corpus to form a summary. We have in this task we have two approaches. First one is extractive summarization and second one is abstractive summarization. Our proposed task based on the extractive text summarization.
In the text summarization, we first we have a goal of the extract summarization is extract and rank set of the top L most significant sentences from the document to present in its a compressed form and summary of the sentences. Here, first we have seen in the structured summarization. Here we have three steps to solve the structured summarization. First step is intermediate representation of the text. Second one is a second score the sentences, and third step in ranking and selection for the sentences to form a summary of the article. These are the potential work on a single document summarization in various Indian languages. In the existing literature survey, we found some issue in the literature survey. We authors use the pre-trained model to solve the issue text summarization problem, but not explore the statistical and algebraic methods for the summarization. And transformer model demands high computation power and large data set, which may not feasible in a low resource scenario. Uh, uh, Statistical and algebraic approaches are computationally lightweighted, making them suitable for the low resource constraint and environments. This is our proposed framework for to solve the structured text summarization problems. So first, we in upcoming slide we explore the each step in the one by one in the upcoming slide. The first one is these are the data sets. These are the data set they provided by the FIRE 2020-24. For these are the languages in Hindi, English, Hindi, Gujarati, Telugu, Kannada, Tamil, Bengali. We have seen in the English have a lot of data set available on the internet, but Hindi and Gujarati, Telugu, Kannada, Tamil, Bengali data set are the low resource language that are not easily available on the website of other resources. So we can solve we can a lot focus on the Indian language summarization. First, we process the data set by removing the missing and duplicate values from the article and summary columns. Then we tokenize the article into sentences and remove the punctuation and empty string to prepare the text for further processing. In the feature extraction part, we have used TF-IDF vector with n-grams. Here we used n-grams by till 4 n-grams. We extract the feature for each sentence in the article. We with n-grams. First, n-grams means 1 gram means single words in a consecutive way, and second word is bigram means is two words, two sequence of the two words in a consecutive like this. Then we applied the SVD on the extract TF-IDF factorization method. We extract the SVD on these extract the latent feature from the article. Then we score of each article of each sentence in the article. Then we select top 15 sentences selected for the summary of the article. Here we ranking the sentences based on the SVD features, and then we generate the summary to select the top 15% sentence of the article. Here we got the result for training data set Telugu, Hindi, Tamil, Kannada, English, Gujarati, Bengali data set. In my proposed model, there is no training part. Here we directly extract the feature. Here we directly score the sentence and extract the top 15 sentences to form a summary. Next, this is the result for the validation data set. Then our proposed model to evaluate our proposed model on Gujarati data set. We got the third rank of this task. And in table number 6, here we also got the third position of the Bengali data set. Next, here we got the fourth position of the Hindi languages, and we also fourth position for the Telugu languages, and we also got the fifth position for the Tamil languages. These are here we capture the in the conclusion. We capture the contextual information by considering the sequence of the word. TF-IDF with n-grams but lacks deeper semantic understanding, reduce the dimension to uncover the latent structure in the text. Extract key features and relationship while filtering noise and redundancy, produce concise and informative summary by leveraging both importance and latent patterns. In my future work, integrating this feature with deep learning can be enhanced the summarization by incorporating contextual and semantic insights. These are the references. Thank you.
Okay, any questions? Okay, thank you, Sangeeta, for your time. Okay, thank you, Sangeeta.
Okay, thank you.
So our next session will be by Andrew Yates, one of our keynote speaker, and it will start at 12 p.m.
So now you
Good
can.
now, you can now, you can now.
Hello. Hi, Andrew, can you hear us?
Yes, can you hear me?
Okay, so I think there are like 3-4 minutes to the talk. So people are still coming in, so we can start after like 3 minutes.
Okay, just let me know when.
Oh, okay. Oh, that's all. That's all. What? They're a meeting. Good talk, okay. Okay. Rest of the people, please come in. Huh? What was it? What was it? So, we are talking. Hi, Andrew. So you can hear us, right?
Yeah, I can hear you.
Okay, right. So yeah, I mean, we are very happy to have you here to deliver us this talk on flexible representations with learned sparse retrieval. I'm sure it'll be a very nice talk. So without much delay, I'll be leaving the floor on to you.
Thanks. Yeah, so my name is Andrew Yates. I'm an assistant professor at University of Amsterdam. And I'm going to talk about this retrieval paradigm called learned sparse retrieval, some of the nice properties of the paradigm, how it compares with others, and some recent work here. But to start off, to motivate things a little bit, I want to think about something that's probably fairly obvious to all of us. And that is natural language is a really convenient medium for input and output of different forms. So for example, we're all familiar with things like Claude and ChatGPT. I can ask, for example, Claude, what is learned sparse retrieval? And it'll give me some definition. It's fine, not great, not terrible. It says that traditional sparse retrieval methods like TF, IDF, and BM25 are related because they match exact words between queries and documents. And it says it also brings in some machine learning techniques that help understand the deeper meaning of text. So this is pretty decent. Of course, because this is a text, we can take this text and, of course, give it to something else. This is not a surprise to us, but it's worth pointing out. So, for example, we can ask to shorten the definition to one sentence. ChatGPT shortens it in some way. Doesn't really change anything. It just puts the bullet points together. But this is possible because we're using this natural language text as our input and output medium, specifically output. And so we have this shared representation space. We didn't get a dense vector or some latent vector out of Claude and have to figure out how to make ChatGPT understand the vector. It just understands it automatically because we're dealing with language. And just to drill down on the point, we can do the same thing, with another chatbot. So we can give a definition to yet another chatbot like Gemini. It was trained totally independently from the other two. And we can ask it to do something like, I don't know, assess the accuracy and completeness of the definition, and it will do that. So these are all models that have never seen each other, yet they can all work together. And the reason they can work together is because what they're dealing with is this natural language text, and they know how to understand the natural language, So, they don't have to have seen each other at training time, so to speak. We don't have to train Gemini to be compatible with ChatGPT and ChatGPT to be compatible with Claude or anything like that. We just have to ensure that they can produce natural language as their output. And this is kind of analogous to what learned sparse retrieval does for these neural retrieval methods. Before I get into that, one more example. There's also these complicated agent pipelines. For example, this is a paper at iClear where you can have, different agents working together in different ways, maybe with different roles. One of them writing code, another deciding how to model a problem, another interpreting the problem, another providing feedback on whether the programming and modeling were successful, and so on. And again, they don't have to see each other. They're just passing natural language text around. So there's no need for them to understand the internals of the other models. Now I'm going to talk about this in the retrieval setting, as I just hinted at. So here we'll have a query, maybe something like Taj Mahal. We'll have a document collection. We'll have a ranking model, and we'll produce a ranked list of documents ordered by their relevance with respect to that query. And then, of course, we can estimate how good that ranked list is with the ranking metric like precision at 3. And so I'm going to talk about learned sparse retrieval in this retrieval setting that I think we're all very familiar with. Now, as I've been hinting at, learned sparse retrieval is different than dense representations in these latent vectors. So to think about how this would work in a dense setting, we have a query like Taj Mahal. We have this dense encoder that takes that query and converts it to a latent vector. And that latent vector has, hundreds of dimensions. Here we have 768 dimensions. The middle dimensions are not shown, as you see with this ellipsis. And these are latent dimensions. So we can point to dimension 1 or dimension 2 or dimension 3. We can look at their values, but we can't really do much to interpret what those values mean. We see, for example, the dimension 1 has a value of 0.2. That value probably has to be interpreted in conjunction with some other dimensions. Maybe we have to look at 1, 2, and 3. And we don't really know what's being stored in the vector, other than there's some latent information that's useful for ranking documents here. With a sparse encoder, as we see in learned sparse retrieval, the output representations are a bit different. So rather than having 768, there's one dimension for every item in the vocabulary. So maybe we have 30,000 dimensions if we're using something like BERT word pieces as our vocabulary. Maybe we have hundreds of thousands if we're using something like white space tokenization. So there are many more dimensions. However, most of them are 0 in most cases. So with that dense vector, we expect to see 768 dimensions, most if not all having non-zero values. With this sparse representation, only a very few of them will have non-zero values, and that's why we call it sparse. So for here, example, if we look at the first 2 dimensions, we see the query terms exactly. We see the weights on those query terms. It's quite clear what's going to happen as far as matching a document. If we look at the 3rd term and the 4th term, we see India and landmark. These are expansion terms that don't appear in the query. But they can still appear in the sparse representation. We're of course not limited to the literal tokens in that input text. And then we see many other terms, most of them 0 and not shown. And then finally a term like dome with a low weight here. So this type of representation gives us something grounded in natural language. And because it's grounded, it's easy to interpret, and that makes it flexible. So thinking about the original motivating example I showed you, where we're passing text between LLMs, we can do something similar here. Because each dimension here is grounded in a vocabulary, it's pretty clear how to treat them. As long as the weights are reasonable, we can do all sorts of things without combining, without training models together and ensuring they've seen each other. We're not limited to the text setting. So for example, here our document could be an image, and our query again could be text. Because it's an image, we wouldn't expect the same representation, but of course that's fine. What we expect to see is that some of the terms are the same. So again, we see terms like Taj Mahal, India, landmark overlapping, and then also some terms that are a bit different. So now we have a query representation on the bottom, and we have a document representation on the top. This is all we need in order to do some ranking. Typically, we would store that document representation in an inverted index, and then we would use a standard query processing algorithm to take the query's representation and score the documents in the index with respect to that query. You can think of an inverted index as a data structure that is very fast at computing dot products between two very sparse vectors. That's not really the normal way an inverted index is described. But if you think about the difference between how dense retrieval is done with an approximate nearest neighbor index for computing dot products between dense vectors, then I think it's intuitive to think of an inverted index as the same thing, but for vectors that are very sparse. And exactly what that scoring will look like, we take the terms that are non-zero in both representations, we multiply them, and we sum all of those products together. So for example, the first term, Taj 1.9 times 1.6, plus the scores for the second term, 1.4 times 1.7, and so on. This is easy to do with an inverted index because we can iterate over the terms in the query. And for every term in the query, we can pull up that posting list or that inverted list in the index that lists the documents containing that term. And that allows us to quickly compute the score for that term. And we simply can iterate over the terms and their lists in that way. So for the purposes of thinking about how this would work at inference, everything is really the same as a traditional sparse method like BM25 or TF-IDF. What's different is that now we have weights that are much more powerful than BM25 or TF-IDF weights, and they're coming from more powerful neural models. So I've shown you the multimodal setting. We can of course also do this multilingually. So this is basically comparing documents and queries of different modalities. So this is enriching the sorts of things we represent with sparse representations. But something else we can do is enrich the representations themselves with different models. So again, I show you this normal sparse encoder as before, normal in quotes because I'm just using it as the default. And this we'll think of as something like a word piece encoder that computes scores for everything in a normal token vocabulary. So these are unigrams, single terms. Now we can bring in another type of sparse encoder, of course more than one if we wanted to. And here we have a sparse encoder that identifies entities in the input text. And so we get something just like before, but our vocabulary is now over entities. Specifically, when I say entity here, I mean a Wikipedia page. So this is kind of like a neurosymbolic representation where we can point to specific Wikipedia pages and say, that page is relevant and it's relevant with this weight. Let's expand the representation. This other page on architecture is also relevant with a lower weight. We can point to that page and expand the representation. And now we can have a single representation of that input by essentially concatenating the types of representations from different encoders. And of course, we could do the same thing analogously on the document side. So now we have a final representation that both describes the input text in terms of normal word piece tokens, but also has this much richer type of vocabulary where we can identify relevant Wikipedia pages and point to them exactly. And as before, once we have this final representation, it's just a sparse representation we can do anything with. We would put this in inverted index exactly as before. All that's really changed is that we've modified our vocabulary to kind of enrich what we can represent there. So to give an overview of these learn sparse retrieval methods before I talk about some specifics. They've been shown to be really effective both in and out of domain. So I'll show you slides later comparing them to dense retrieval, both on standard data sets like MS Marco and deep learning, and also on generalization data sets like BEER. And in both cases, they're on par with dense retrieval methods of a similar size. Because they're sparse, we can take advantage of existing indexing and existing architecture in production, in academic settings, anything that already supports an inverted index. And so they can be very efficient. There are some issues I won't get into with this talk using totally standard inverted indexes like Apache Solr, the standard Lucene approach. These methods work well with them. They'll just slightly slower, a bit slower than if we were to store BM25 or TF-IDF vectors, because these sparse representations have different weight distributions than we get with TF-IDF. So think about something like going up from, tens of milliseconds to maybe 200 milliseconds response time for the query. So there's a lot of more recent work addressing this problem, coming up with much more efficient inverted indexes. Basically looking at the properties that these sparse representations have and changing how the query processing works a little bit, how pruning works, how the block max optimizations work in order to make sure they're just as efficient as something like TF-IDF would be. And finally, it's a really efficient representation type. So we can store all sorts of things as a sparse vector, and we can easily understand what's in that sparse vector because it's transparent, it's grounded in natural language. So this talk will have 3 sections. The first, I'm going to talk about kind of the mechanics of how these representations can be created, investigate whether they're grounded, and give you some comparisons with dense retrieval methods, just to satisfy you that they are on par. We're not losing very much by moving away from this latent setting. After that, I'll talk about some work enriching the representations with entities that I hinted out earlier, and then also some work encoding images as sparse vectors, because this is a more challenging setting. So first, the overview. Learned sparse retrieval method has a few ingredients. Here we'll talk about 3 very briefly. The first is something that takes that input text and creates that sparse vector. This is the sparse encoder. So this needs to take text like Taj Mahal and say, Taj has this weight, India has this weight, landmark has this weight, and so on. A sparse regularizer is used during training to ensure that vector that comes out is actually sparse. I'm not going to go into these in detail, but a very simple way to do this is simply to take the top K weights during training. So we always take the top 100 weights, and this ensures that most of those 30,000 or so other weights are 0. And it forces the model to use the weights wisely, so to speak. There are, of course, other ways to do that besides top K. So typically something like a flops or L1 or L2 regularization is used just to encourage that vector to be as sparse as possible. The details of this aren't so important, though. If you're familiar with regularization, you get the idea. The third ingredient is we need some way to supervise the training process. These are, of course, neural models. They're trained with gradient descent, some optimizer like Adam, usually. The supervision here looks just like it would with dense retrieval. So we have things like negatives, hard negatives often come up. Some things like teacher distillation from a cross encoder often come up, and so on. From the supervision perspective, it doesn't really matter whether the encoder is sparse or dense. Either way, the same supervision can be applied. So I'm not going to really talk about that other than to say that this is the same as with training other types of neural retrieval methods. But what I really want to talk about here is the sparse encoder, because this is the most unique ingredient, and it'll give us some idea of how these representations are created. And then comparing different types of encoder will allow us to satisfy ourselves that these representations actually do create vectors that are grounded in language. What I mean by that is that each dimension has some actual meaning. We can interpret this dimension as being about a monument or a landscape, and so on. So the simplest type of sparse encoder we could use, we'll call a binary encoder. This simply tokenizes the input text. If a term is in the input, it has a 1 in the sparse representation. If it is not in the input, it has a 0, and that's it. There's no learned machinery here. It's just a tokenizer. So there's no opportunity to weight the terms, and there's no opportunity to expand the representation, meaning every term that appears in the representation also had to appear in the input. So for example, we see terms like Japan, landmark, dome don't appear in the input, so they have zeros here. We, of course, want to do something more sophisticated in practice. So the next thing we can do is enable some form of weighting. To do this, we can use what we call an MLP encoder. And this is basically just an MLP on contextualized term embeddings that predicts their weights. So as before, we tokenize the input text. Now it's fed through some transformer layers to produce a contextualized embedding or a hidden state, one of these vector outputs for each of those terms. So we, for example, have a vector for Taj, we have one for Mahal, we have one for India, and so on. We applied that MLP to each of the vectors to predict their weights, and then we put those weights in a sparse representation. So as before, we have no expansion. Only terms that appeared in the input appear in that sparse representation. But now we have some weighting on the terms, so we can decide, for example, that the term India here is a little less important for matching than that entity Taj Mahal. Terms like Dome, Landmark, and Japan, of course, still have weight 0 because we're not doing expansion. Now, if we want to enable expansion, a typical way to do this, there are other less popular ways that I'm not going to go over in this talk, is a masked language modeling encoder. So by masked language modeling, I'm referring to this mask filling objective that encoder methods typically, transformer encoder methods typically use, like BERT, Roberta, Electra, not Electra, but BERT and Roberta, things like that. I'll talk a little bit later about how this relates to the language modeling head used by modern LLMs. The very short summary is that they're essentially the same for our purposes. So we have this language modeling head. Here it's a masked language modeling head. This takes those vector representations from the transformer, just like the MLP did. But now, rather than predicting a single score, it predicts one score for every vocabulary term. So that gives us one set of scores over the vocabulary for each input term. And then typically these are aggregated with some sort of max pooling. Typically there's some sort of ReLU so that scores below 0 become 0. And then this ultimately gives us a representation that includes both terms that appeared in the input as well as related expansion terms that were not there. Japan there should have a score of 0. So terms like Dome and Landmark are expansion terms that were not there in the original input. So the first thing we can ask is whether these representations are actually grounded. So I said they correspond to language. Can we do an experiment to establish that actually seems to be the case? So the notation you see on the left, for the document, we're using both expansion and weighting. That's this MLM encoder on the right that I just explained. On the query, we're using no weighting, so we're using only a tokenizer. We see results like this. So the point being, with only tokenization, with no opportunity to expand, document and query can match against each other. I'll show you a comparison point shortly, but these results are pretty reasonable. So it's possible not to even use a GPU at query time with this setting. Of course, if we enable weighting on the query side, we can get results that are a little bit better. And if we enable expansion as well, we would again get results that are a little bit better. But the point is, we get very close to the maximum results with no weighting or expansion at all on the query side, only with tokenization. This suggests that the representations are grounded because there's no opportunity for terms to lose their meaning, so to speak. There's no way for the query to store anything in the term India but the term India because there's no learned machinery. There's no opportunity for it to do otherwise. And this means the document has to as well if it wants to match the query. Now I've been promising a comparison with dense retrieval methods. Here we have Colbert, Splade v3, and this Dragon Plus method. The reason I chose these is these are the highest results from the dense retrieval methods that I'm aware of that are using a BERT size architecture. There tends to be a lot more work on dense retrieval. This is, I think, quite an opportunity to do for learn sparse retrieval, but there tends to be more work with dense retrieval. And so there are a lot of huge LLM-based methods that just haven't been applied to sparse retrieval. Though, as I'll show you in 2 slides, they easily can be. So anyway, these are 3 models of comparable size, looking at 3 data sets, MS Marco DevSet, the Deep Learning 2019, and the Deep Learning 2020. What we see is that the models are quite close across all 3. Splade v3 is slightly better on the first, about equivalent with Colbert on the third, slightly lower on the second. And then we see a similar story if we look at any of the dense methods. Colbert is consistently pretty good, but these are very small differences overall. Something like in the middle case, 72 versus 74 in DCG. Both are quite high. We can do the same type of comparison in an out-of-domain setting, where the models have been trained on MS Marco and then applied to other tasks. For whatever reason, models based on per-term representations like Colbert and like learned sparse retrieval tend to do very well here. I should mention Splade uses the MLM encoder of both query and document, so it's expanding queries, it's expanding documents. And we see essentially similar conclusions, where depending on exactly which of the beer data sets we look at, one method might be slightly better than the others, but overall they're pretty comparable. And it's not the case that any of these is significantly and consistently lagging between the others. In fact, here I think learned sparse retrieval is the best for the majority of them, but of course there's some cases like Quora in the middle where it lags a little behind. So all this to say, it's a very effective approach comparable with dense retrieval. So given that it's comparable, I think it's worth thinking about how dense retrieval works and how these language modeling heads work. So I want to make two arguments here. The first, that there's a close relationship to dense retrieval, and the second is this masked language modeling and language modeling heads are essentially the same. But first, we'll look at dense retrieval. So we have some query. We encode that with a transformer that gives us out a query embedding, which is a dense vector. We've done the same thing for documents already. That gives us a lot of document embeddings. And now we can compute scores between that query embedding and document embeddings with the inner product. So that gives us some document scores. If we think about how that masked language modeling head looked, it's actually quite similar. So we have something as before with these transformer layers taking the text as input. When we're doing masked language modeling, as BERT pre-training does, we have this mask token, and that's what we're using as the query, so to speak. We have this masked language modeling head here. This is nothing particularly complicated. So there's some projections and some layer norm inside. This gives us a dense vector as before. This is really analogous to the query. And that dense vector is compared to every term in the vocabulary, which are analogous to document embeddings. So for example, we see something like Mahal having a very high score, some other vocabulary term like tours having a much lower score. So these term embeddings and document embeddings are quite similar. What's going on here is almost like dense retrieval over a vocabulary, and then after deciding on relevant vocabulary terms, they're added to a sparse representation. Now, modern decoder models use the language modeling head rather than masked language modeling. So they try to predict the next token rather than trying to fill in a mask. This is the language modeling head. Really, that's analogous to how a masked language modeling head works. The difference is just how it's applied, but the heads themselves are very similar. And as before, there's some dense vector that comes out of that head, and then we're using it to compute scores over a vocabulary. So now we've taken a look at some basic ingredients of LSR, compared it to different methods. I want to talk about how we can go further in two ways, creating more powerful representations and then creating more powerful models that can represent different types of input. So one potential issue with these representations is that it's a bag of words, of course. And is this what we really want? Do we really want this word piece vocabulary? So here we see terms like member, who, and us. But actually, these terms are US and WHO because here both are acronyms. So this is the issue of homonyms, where something like US as United States and us will be stored the same way in the sparse representation, even though they have different meanings. One way to address this is by enriching the representation with some sort of entities, like I hinted at earlier. Another issue that can happen is that because we're using a word piece vocabulary typically, these terms can be broken into many smaller pieces. So here we see chunks like NTE, CH, bio, shot. It's not totally clear what is being stored here. And in this example, it's BioNTech shot. So that first word has been split up into several word pieces. We could have collisions. We could have other terms that are also split up into CH. And now it's hard to indicate whether that CH came from BioNTech or came from another word like March, for example. So one way to address this issue of collisions would be to change our tokenization to say that we'll do something like white space tokenization and keep these as full terms. So there is work doing this. For example, you can define some new vocabulary and you can run MLM pre-training on top of it. So now you have a mask language modeling head compatible with your new vocabulary, and you can encode queries and documents using that. This solves the problem of collisions, but it doesn't really solve the issue of homonyms. So we still don't know if US is United States or us. In order to address both of these, we have this paper, DIVO, Dynamic Vocabularies for LSR with Entities. It was just published at EMNLP a little over a month ago. And here, the representation, as I've shown earlier, is expanded with Wikipedia pages, essentially, so entities and concepts. So we still have a term like us, but we can also indicate with some confidence that us here should refer to United States, because we're talking about the World Health Organization, the WHO. This approach has two ingredients that make it possible. The first is a candidate retrieval step where we identify related entities. After identifying the related entities, we use some sort of entity representation in order to score the entities and decide whether they should be placed, whether they should have non-zero weights in that sparse vector, analogous to this mask language modeling head. So we essentially have this dynamic vocabulary head that works with a varying set of entities in order to assess their relevance, doing both expansion and weighting as a mask language modeling head normally does. So I'll show you some experiments looking at this in a few different settings. In these experiments, we're going to use an EPIC or SPLADE variant as our standard LSR model. So this is doing query expansion on the document side, and it's doing weighting only on the query side. So it's using that MLP encoder. We're going to add these Wikipedia pages, essentially, as vocabulary items to that base model using the dynamic vocabulary head. We're going to look at some entity-rich data sets, things that mention non-common entities quite a lot. We'll train both types of models using only synthetic queries, so no in-domain training data of any kind. And then we'll look at different types of candidate selection, whether we choose entities that were only in the input text or whether we retrieve related ones. And then we'll look at different ways to embed those entities. So first, looking at results in the base setting. The blue bars will be with word pieces only, and the orange bars are going to bring in linked entities. So this means identifying only terms that were directly in the input that correspond to entities in Wikipedia. We're not considering any sort of expansion beyond the input. And then those entities or Wikipedia pages will be represented with this LAC paper that produces essentially embeddings using a dense retrieval encoder to create the vectors for every entity. And we see a pretty consistent improvement across data sets with this default setting, but we can see a larger improvement depending on how the method is used. So we can look here at different ways to select candidates. As I mentioned, we were using REL before. That's only looking at entities that directly appear in the input text. We could also even just use BM25, so issuing that text against a Wikipedia index, identifying the pages that are returned, and using those to add to the sparse representation. This is a little bit noisier than linking, but it works nearly as well. I think what's more interesting is using LLMs to look at that query and to generate a list of entities or Wikipedia pages that could be relevant. So here we see Mixtral, here we see GPT-4. And these are substantially better than the other approaches. They're identifying a lot of useful entities, and they're identifying entities for expansion. So things that go beyond exactly what's in the input. I'll show you an example of that shortly. And we can also ask a human, of course, to identify the Wikipedia pages or entities in that input. And this is similar to GPT. I'm not going to argue that GPT is human level in general. But here we have a really recall-focused task where we need to come up with all sorts of entities that could be related. And large language models are really good at that task. Because we have these two steps, the filtering happens after candidate selection. It's not important that the list of entity candidates has high precision. What we actually need there is recall. Just to show you an example of both what GPT-4 finds in comparison to human and what expansion looks like. If we have a query, this is from Codec, about French support during a Revolutionary War, GPT-4 finds individuals who are related to that, like Benjamin Franklin. It finds specific battles like Siege of Savannah. So these are clearly expansion terms. This goes beyond, the Wikipedia pages mentioned directly in that query, like French and Revolutionary War. And then we see the same thing for something like NFTs, where GPT has a lot of much better recall. It finds a lot of kind of more generic terms that a human probably wouldn't think of. I might say like cryptocurrency, but things like digital asset, decentralized application are more recall oriented, I think. The other thing we can do is vary the types of embeddings we use here. So again, looking at word pieces in LAC, the default setting. If we use LAC is based on the Wikipedia descriptions of entity. So it's taking the description paragraph from their Wikipedia page, it's encoding that as a vector, and then that vector is used to represent that entity in our dynamic vocabulary. We can also look at input token. So this only fixes the problem of collision. It doesn't really make the representation richer. It just makes it less ambiguous. So this is a small improvement, but we can see a lot of the improvements is coming from making the representation richer in the sense that it has additional information about entities that are brought in by these representations. We can look at another way to encode the Wikipedia page, performs fine. We can do something really simple using Wikipedia to vec over the Wikipedia pages where entities, so page names, are treated as separate tokens, so we get a representation out of them. This is really simple, but it works surprisingly well. And then if we use some sort of sophisticated entity representation method from Facebook, this Blink encoder, we get a little bit better than the other description-based methods. So now I want to really briefly talk about a more rich type of input. I just talked about a more rich type of representation, which is the multimodal setting. So what we want is we want to take some image like this, and we want a sparse representation of the image that has terms like animals, boy, umbrella, and so on with sparse weights that correspond to what actually appears in that image. This paper that I'm going to talk about is not the first to do that. There's some large ones from other groups. So for example, this LexLip paper uses a really large architecture, 13 million training pairs, 8 GPUs, and it is able to create a sparse representation of the images. Unfortunately, they didn't release the checkpoints. What we're going to do in this work is try to have a really lightweight formula for creating representations from an existing model. The idea being we already have models like CLIP that are very good at representing images. And so we can take a dense vector from CLIP that should already represent what's in the image and simply create a sparse vector out of it that takes that latent representation and grounds it in language in some way. So to do this, we'll create this dense to sparse layer. We'll freeze the caption encoder and the image encoder from a model like CLIP. We'll train only this new layer, and then we'll use that layer to produce a sparse representation from the existing dense one. The challenge here has to do with grounding. It has to do with making sure that the dimensions in that representation are actually meaningful. So here we see an example of when things went off the rails. It's not meaningful. We see terms like ship. There's no ship in that image. We see terms like accent. I don't know how that could be related, like DE, like NA. Wild is vaguely related. And so what's happening here is a sparse representation is being produced, but the dimensions of that sparse representation are not actually anchored in any existing vocabulary. So they're just totally latent random dimensions, sort of like you would see with a dense vector. This is, of course, not what we want, because if we have a method like this, it won't be compatible with other sparse vectors that are grounded in language. In order to get the flexibility we want here, we need the representations to all be created in a way that they have some meaning to each dimension. The way that's tackled in this work is just with an expansion schedule. So if we think of those different types of encoder, we can essentially turn on and off expansion by choosing the encoder we use. So here we're modifying the MLM encoder to disable expansion sometimes during training. And the key point here is if expansion is not allowed on the text side with the query, then the only terms that can match the query have to be terms that are also in the query. So it's not possible to expand to a term like accent and decrease the loss. Of course, this limits the performance of the model because we would like expansion in order to maximize it. So we have this schedule where during training, we increase the amount of expansion that's allowed over time. If we look at results, taking one blip model as an example, this is a clip variant from Salesforce. This is on MS Coco, image caption retrieval, similar results on this Flickr 30K image caption retrieval. And we have about 0.57 with blip. If we train with weighting only, so no expansion schedule, the model does work, but we have a significant performance decrease. We've gone from 57 to 47 precision at 1. If instead we enable expansion using our expansion schedule, it's comparable to the initial dense vector, except now we have a sparse vector that can be used with different modalities and combined in various ways. We have something that's fairly reusable. So this expansion schedule allows us to convert that dense vector to a sparse vector with minimal loss and performance. So that brings me to the conclusion of my talk. Thank you for listening. So learn sparse retrieval creates these flexible, grounded representations for queries and documents, as I've been arguing. We can do this in a multimodal setting where we have a sparse vector anchored in language. We can do it in a text setting, and we can do it with dynamic vocabularies and other ways to enrich the representation, giving us different ways to augment this vector in a neurosymbolic way. So essentially here we're pointing to specific Wikipedia pages that can be used to disambiguate and represent and extend that representation. So thank you for listening. That brings me to the end. I'm happy to take any questions.
Thanks to the speaker. Andrew, can you hear me?
Yep.
Can you see me as well? I think you can see me, right?
Yes, most of you.
Yeah. So yeah, thanks for the wonderful talk. I have maybe a very foundational question or fundamental question. So sparse retrieval, as we know, it usually works well with term weighting models like PM25 language modeling. Whereas I guess that with learned sparse retrieval, it's just an inner product between the vectors that you usually compute, right? Now, my question, although not directly related to your talk, is like, I want to hear your comment on what do you think is the scope of coming up with novel term weighting approaches? Maybe hand engineered ones, but that could potentially work better for learned sparse retrievals. What are your thoughts on that?
Yeah, the scope for how we can weight these differently. I think it's kind of analogous to dense retrieval in the sense that there's some really clear ways to do things, and we have limited places to look for improvement beyond that. So like with dense retrieval, you have some sort of architecture like BERT, or maybe you have an LLM. You'll use that to produce a vector. And really the innovation that's happening, I think, is in different loss functions, different ways to train that model to produce the right vector. But we don't have a lot of room to change the architecture that's producing that dense vector exactly. I think learned sparse retrieval is similar. So there's a few choices we can make for how the vector is produced. So we can use like this MLM head that does expansion. We can use something like the MLP that's doing weighting. We can maybe use something that does dynamic vocabulary. But there's, I think, there's somewhat limited places to change the architecture beyond that. Now, because it's sparse and transparent, if there's something we know we want, then we can make some, targeted changes. So I kind of showed you where we motivate the idea of pointing to Wikipedia pages here until we know we want this in the output. And so we can come up with some additional machinery, like a new encoder to do weighting over that type of Wikipedia page. So I think it's a little more rich there in terms of places, to look to create new types of weighting. But overall, I don't think, it's that easy to come up with new approaches for this, similar to how everyone, uses BERT or uses Mixtral or something for dense retrieval. Yeah.
For the answer, are there questions for Andrew? What's up?
Hello, can you hear me?
Hey, yes, I can.
Yeah. Hi, Andrew. Thanks for the talk. So I just have a question. So do you think that this performance of the retrieval models that depends on the tokenization? Means how effective this tokenization is to improve the performance of these rankers or the first retrieval model?
Yeah, that's a good question. I think the tokenization does have a role to play. I've been surprised that it doesn't play a larger role because, these collisions, for example, can happen very easily. I guess people don't, for example, issue queries with Roman numerals in them normally. But if you had like three different numbers expressed as Roman numerals, and then you stored that as a bag of words, the XV would get split up into two tokens, and the IV here would get split up into two tokens, and there would be no way to actually match the numbers at all. That's an extreme example. But if you think of, these medical terms, they also have character engrams that can overlap. You can have term A with these three character engrams and term B that shares two of the same ones. And now they've kind of collided in the representation because you don't know which term those dimensions came from. So I think it definitely does affect things. But it seems like it's not a huge problem, I guess, because there's a lot of other contextual information about what's occurring in that query or document. And so the other terms can kind of disambiguate that. But I think this is something that's pretty interesting to explore. There was an ECIR paper last year on corpus-specific vocabulary from Antonio Malia. I didn't mention it in the talk, but they show some improvements, essentially trying to tailor the tokenizer to the specific vocabulary they're using, which also deals with this collision problem I'm talking about.
Okay. Yeah, sure. Thanks.
Any other questions for Andrew? Okay, maybe a last question that I have one for you. So if you think of this learned first retrieval space, right? There is no concept of the collection statistics as we normal like BM25 or language model, the normal sparse indexing. There's something called collection statistics, which is not there, which makes it quite difficult to interpret. Like, so we have like the importance of terms manifested in collection statistics, but here we don't have any such thing because everything is collapsed into one weight. And we're not really sure, if it's a contribution from a document or from the collection. So do you think like there could be ways in which we could separate them out and maybe have like better out of domain generalization for different type of collections?
Yeah, so I think both TF-IDF and these weights are trying to get some notion of term importance within a document or a query. They're just going about it in different ways. So you're right, here we have a kind of opaque model that's generating the weight. So we can look at that weight and say this term is important, but we really don't know why. So I think this definitely could be improved upon. There is work that uses TF-IDF in this space also. So for example, maybe for the query representation, you use a TF-IDF representation. And then for the document, you have this as learned representation from a neural model. This is interesting, but I think it's something that's relatively underexplored. I think it would be really interesting to see how this could be improved and, anchored more in the corpus. I mean, obviously you could do something like pre-training on the corpus, but maybe there's a more explicit way to kind of anchor the behavior on exactly the patterns you see in some specific collection.
Right. Thanks a lot for the answer. Are there any more questions? If not, then maybe we can close. So thanks a lot for agreeing to talk in FHIR. You were supposed to come, but then you couldn't come due to some last moment things. But maybe next year, we hope to see you in person, right?
Yeah, I'd love to come in person. Thanks for inviting me.
Thanks a lot, Andrew. Bye-bye.
Hi, am I audible to the online participants?
Yes, ma'am, you are audible.
Yes. So shall we start? We will start with your presentation. Aruna and Abhirami, can you please share
Yes,
your screen?
One second, I'll share my screen. Ma'am, screen sharing option is not available.
Okay, just give a moment here. Yes. So good afternoon, everyone. We will start with our second round of track presentations on the conversational agent for GI cancer track. And we will start first with our online presentation from SSN College. So now we can share your screen, Oruna and
Abhirami, ma'am, yes, ma'am, 1 second.
Abhirami. Yeah.
Ma'am, is the screen visible right now?
Yes. Yeah, I think it's loading here.
Sorry. Here. So our topic is gastrointestinal cancer related question answering.
So before you start, you have 5 minutes and
Okay.
last 2 minutes for question answering. Yes. Please.
Okay, ma'am. Thank you, ma'am. I'll proceed. So our topic is gastrointestinal cancer related question answering using BERT. Myself, Abhirami. My teammate is Aruna. We did this project under the guidance of B. Bharati ma'am. Our team name is SSN Gen AI and paper ID is 55. So the problem statement given to us was we have to answer the questions asked by the user about gastrointestinal cancer. It might be under varying topics like causes, symptoms, genetic mutations, and treatment. So the data set provided, Aruna, would you like to take on?
Yeah. So we wanted to collect information about 8 different types of gastrointestinal cancer in a detailed manner. So we collected our own data set by collecting informations from online data sources such as Wikipedia and other available journals and articles. In our data set, we have information about the 8 cancers such as symptoms, causes, genetic mutations, diagnosis, and treatments. We have stored it as a paragraph so that it will be easier to be put into BERT and get our answers from the question.
The sample data set is provided.
Yeah. So the methodology which we have followed is, so first we have prepared our context and select the context that matches with the specified cancer in the question. And then we simplify the question by extracting only the information related to cancer. And then we split the context into 3 parts, which we call as chunks. So the reason is that the BERT model can handle only about 512 tokens. Since our data is large, we have to split it and parse each of the chunks and then calculate the score for each of the answers from each of the chunks. And then the one with the highest score is considered as the answer.
So, implementation, we have used the BERT model, which is trained on SQUAD dataset. SQUAD expands to Stanford question answering dataset. Here, as mentioned by Aruna, the given context is divided into 3 parts. The first part consists of both the causes and the symptoms. The second part consists of genetic mutation, and the third part consists of diagnosis and treatment. So the question, the cancer related part of the question is extracted or is tokenized along with, and all the 3 parts are parsed and a score is provided for each part. So based on the maximum score which is obtained, we print the answer. But if all the parts provide an answer, the maximum score is 0, then the answer which is provided is sorry, I was not able to discover the answer. So sample result is provided for the question about BRCA mutation in pancreatic cancer. And they have the question asks about its potential implications and treatment. So here and here. So in order to calculate the performance metrics, we have used the Rouge score and the Blue score. As you can see, the scores are quite low, but this is because there was no training model or data set that was provided and challenges faced.
So, some of the challenges that we have faced is um, so the token limitation is the first one. Since BERT can handle only 512 tokens at a time, we have to split the context into multiple parts. This caused some problem, and the limitations of the model in BERT, because BERT can extract the answers from a given context, but cannot reason directly. The BERT model that we have choose, it cannot produce its own reason, but it can only extract the answer from the given context. And if the answer is not present, then it is not going to give the answer, even if it implies some answer. And then we have used a pre-trained model pre-trained on SQuAD dataset. Since it is a general data set, it is not quite familiar with the medical terms. And we had no proper training data set of the cancer question and answers, which sometimes produces wrong answers.
So conclusion, we have developed the BERT model, which answers the questions related to gastrointestinal cancer. So this model has a large scope for improvement in ways like it can be trained on larger data sets, and also other models like Llama, etc. can also be used. We used BERT model because we did not have GPU and there were certain limitations, certain other limitations. But Llama and others have a large number of parameters which can help to grow this model for future references or future uses. So future work, other models can also be used, and real-time optimization and handling ambiguity. Instead of providing, sorry, I was not able to provide the answer, a more relevant answer could have been asked, or more like a chatbot could have been developed in order to provide the user with a seamless interface or easier access. Certain references which we used. Thank you for providing us this opportunity. So, ma'am, can I stop sharing?
Yes. Thank you for the presentation. Any questions? Okay, then we move on to our next presentation. That is by Team Cancer Answer on their text items. Sorry. Yeah, your paper topic is cancer answer. Yes, please.
Hi everyone. So I am Shubhankar. So this work has been done with my colleague Aniket, and the title of the paper is Cancer Answer: Empowering Cancer Care with Advanced Large Language Models. So as we all know that GI tract cancer contributes significantly to the global cancer burden, with early diagnosis being crucial for improved treatment outcomes. And the complexity and overlapping symptoms of GI cancer often lead to delays in diagnosis and suboptimal treatment strategies, making timely and accurate information retrieval and also accurate answer to the cancer-related queries play a crucial role in diagnosis, treatment, and patient education, directly influencing health outcomes. So in this work, we tried to explore GPT 3 Turbo in the zero shot mode, which is actually used in zero shot mode, enables precise and contextually relevant responses to cancer-related queries, aiding in better decision making. So this is the task definition, which is already discussed. So we need to actually develop a question answering based conversational system that can provide answers to queries related to GI cancer. And there were 30 queries in the training set and the 50 queries in the testing set. So as we have used the zero shot mode, the GPT model in the zero shot mode, so that is why we haven't used the training set. We just use the testing data set. So this is the overall flow diagram. So user need to give the just prompt to the GPT 3.5 Turbo and it will provide an answer for that. And there are 3 submissions from our team. So first one, we just prompt GPT 3.5 Turbo in the zero shot mode in the temperature 0.7. And the prompt we have used was generate an answer that includes the key ideas corresponding to the question, and the question was given, so which is in the test data set. And in the second one, so we also use this GPT 3.5 Turbo in zero shot mode in same temperature, which is 0.7, and we just passed the query which was given in the test data set. And in the third submission, we also use this same model with the same temperature, and the prompt was to please summarize the key ideas of the answer to the following cancer-related questions in one paragraph given the question. And this is the overall GPT 3.5 Turbo model. And as there were no metric actually no gold standard data set, gold standard answer for that. So we were told to measure these 2 metrics. So first one is the A1, so which measures the fraction of entities present in the model generated answers, which also present in the gold standard answers. So this is the formula for that. And the second one is the A2, so which measures the linguistic correctness and meaningfulness of the model generated answers with respect to the gold standard data. And we have measured those using human evaluation. So these are the results of the submitted run files. For example, the A1 is for run 1, the score was 0.354. And for run 2, it was 0.452. And for run 3, it was 0.546. And similarly, the A2 score was 0.622 for the run 1, 0.702 for run 2, and 0.881 for run 3. So this is the conclusion. So LLMs offer generalization across medical topics, so minimal data requirements and dynamic adaptability, so making them suitable for clinical decision support, especially in the resource limited settings. And also sometimes current LLMs may struggle with highly specialized medical cases, indicating a need for further fine-tuning with domain-specific data to improve accuracy and reliability. And also we need to continue refinement of LLMs. Integrating additional knowledge sources holds the potential to enhance cancer diagnosis and ultimately improve patient outcomes and healthcare efficiency. Thank you.
Two presentations for this chat because the other participants they wasn't present. So I would like to start with the
Back to the next track, we move to hate speech again. And we have 2 presentations in this slot. And actually, the first one is again by Supankar? By his Aniket. Oh, okay, yeah, sure. Aniket Leroy. And we have now most recent approaches here, the zero-shot learning now with unleashing ChatGPT 3.5 to combat hate speech on X. And please, we look forward to your presentation. And it's co-authored with Supankar, so at least that I got correct.
So I will be presenting Hate GPT, unleashing GPT 3.5 Turbo to combat hate speech on X by Aniket and Supankar. So let's start. So the task was, we are given English tweets. We participated in task 1. So we are given English tweets and we had to classify them into hate and offensive or non-hate offensive categories. And we use the GPT 3.5 Turbo model to classify those tweets. And we took 3 runs. So we'll discuss them. And the scores were in the range of 0.75 to 76. We'll discuss the methodologies and results. So the data set was 888 tweets for the test set. So only the test set was provided to us and no training data was provided. Next, the task definition. The task is categorizing automated classification of social media content, specifically tweets, into distinct categories, hate and offensive. And the short abbreviated form is HOF, and non-hate offensive, short abbreviated form NOT. The objective is to develop the model that can accurately identify HOF and NOT categories of tweets. So we basically so the reasons why we are using GPT 3.5 Turbo, 4 short reasons: contextual understanding capabilities of GPT 3.5 Turbo without any form of training, without any form of further training, flexibility and adaptability to various types of situations, and multilingual nature and code mixed handling nature of GPT 3.5 Turbo because of the large amount of pre-training that it has gone through, and efficiency in deployment in any real-time situations. So the methodology, we used a simple prompt. Please check the tweet is hate offensive or non-hate offensive. Only state hate and offensive or non-hate offensive. And then after getting hate and offensive or non-hate offensive, for every tweet, we converted the hate and offensive to HOF and non-hate offensive to NOT, and then submitted our runs. We ran the model at 3 different temperature values, 0.7, 0.8, and 0.9. And this was our simple architecture, zero-shot prompt allowing the social media post. The internal architecture is of a GPT-based model or transformer model, and the final output that we got is HOF or NOT. Next is the macro F1 scores. So there are slight variations among the runs, and the highest value was obtained for 0.7 temperature value of GPT 3.5 Turbo. And so our team ranked in the 5th position, and there was a minor variation of the results are due to the change in the temperature value, and all the range was between 7.75 to 0.76, and there were minimal differences between the runs. So coming to the conclusion, there are further areas for improvement. The complexity of the language, the nuances of the context, and evolving nature of the online discourse requires continuous refinement of the models, and the future research needs to focus more on multilingual and handling multilingual and code mixed content more effectively, as well as on developing strategies to address the subjectivity present in the tweets. Thank you.
Audience? I would like to ask, you have the changes that you made to the temperature are in a limited scope. Huh?
Yeah.
What would you expect if you really go to the extremes?
Okay, so we are given 3 runs. So that's why we tried 3. But if we are given more runs, maybe we have tried more range.
Maybe you can try again.
0.1, 2.9, 1, 1.0.
Exactly. No, but maybe you could do also some experiments after the share task and then compare and stuff. That would also be very interesting, and
Yeah.
report about it. So maybe that's a good opportunity, for future research. Other questions? Okay, then thank you again.
Thank you, sir.
Second part. Please. It's Kavya. Yeah. Okay. Better for me to read. Kavya, for zero shot and multitask learning again. So again, zero shot and large language models approach. Please.
Good afternoon to all. Myself Kavya Ji, and from team MUCS. I'm here to present our paper titled Zero Shot and Multitask Learning Synergy for Robust Hate Speech Detection Across English and Bangla. So the authors of these papers are Kavya Ji, Asha Hegde, Soniti Subramania, and H.L. Shashireka from Mangalore University. So about the task, it is like to find hate and offensive content detection. The task in the task one, it is a binary classification where the train data as well as the development data which will not be given. So we have addressed this as a zero shot learning approach by using the label description, which will be built upon the label descriptions. As well as a task two, we have introduced a multitask learning approach. So under the task one, we propose 3 of the models by using the zero shot learning. We have used the 3 label description approaches. One, it is we have collected the previous HESOC 2021 data set for label description, as it is said that there are 2 classes, that is a hate and offensive and non-hate and offensive. So for that, we have collected the previous data set for creating the label description. So once we have collected data set, we have done the pre-processing. Then further, we have considered it as a label description. And the second case also, we have done the same thing. But here what we have done, it is in that cases, so whatever the collected data from that, we have removed the stop words, which are the data set which we have collected, which was Hindi English data set. So after that, what we have done for taking a text representation, we have used the Hingbird model. And in the next third one, we use the same thing, like we have extracted the keywords by using the TF-IDF, as well as we have manually created 10 keywords for obtaining the label description. In the first 2 zero shot learning, we have used the cosine similarity for predicting the highest similarity for the labels for the test instances. And the third one, we have used the NLI model, that is distill embed model for NLI approach. Next, for the task 2, we can see the framework for the task 2 multitask learning. So here we have submitted 2 of the models by changing the text representation. For the text representation, we have used BERT as well as distill embed, and which will be given to the LSTM. So some of the hyperparameter which are used for the MTL classifier, which will be seen in the table 2. So among the submitted models, the performance of the models, what we have done, it is like for the zero shot learning. For the first task, we haven't given the train set or the development set to check the performance of the model. But what we have done is whatever we have collected, in that half of the data we have used for validating. So out of that, we have shown in the table 3, which will be giving the performance on the validation set. Whatever the submitted models for the test set, so the result which will be seen in the table 4. So among that models, whatever we have submitted for the task 1, we have obtained a macro-reference score of 0.5653. That is with the keyword, whatever the keyword extracted with the label description, the merged one. By applying the cosine similarity, we have got 0.5653, which we have secured a 7th rank for the task 1. And for the multitask, we have got 4th rank for the first, that is offensive gold, and target for the target gold, we have obtained the first rank, obtaining the macro reference score of 0.67 and 6761 and 0.3975. That is for the distal Lambert text representation. As to conclude, we are going to explore more on the zero-shot learning as well as multitask learning approaches. Thank you.
So, yeah, any questions first from the audience? So I think this was quite a unique approach in the 6 years of HASOC. We never had this, to look at the task description and embed it and then compare it to the tweets. No? So really quite unique. And it's almost like a zero-shot or a zero-shot learning talking to the Roberta model, right? That would be similar to the large language model. Right? Yeah, interesting. So would you also consider that the task description that we provide could also be a prompt for a large language model? Could also be used. So your approach is even computationally more difficult, not more hard to implement than just using simply a zero large language.
We have considered the descriptions and that to say that which is HOF, which is not HOF. So we have collected only the previous that data set which will be similar for these tasks, like as they it is been described, like it will be having an English data set, maybe it may contain a Hindi data set also, like mix of these. So we could not find more on that, so we have used that.
Okay, yeah, it's as I said, interesting approach. Really nice. Nobody has thought about this so far. So we're exploring continuously new ideas here for the space of the solutions that are possible. Yeah. Any questions? If not, I thank you again and thank you again, and also especially for the coming and for the participation also in the HASOC track and all the other participants. Very much. So, with that, I think we conclude this session on hate speech, and we move to the next track. Excellent. And I can directly handle the microphone. Gustav.
Thanks, Thomas. Okay, so let's start the script of your track. The first participant is basically Aniket or Shubhankar. So, have you uploaded your slides?
So now we'll present Crypto LLM, unleashing the power of prompted LLMs for smart QAnon and classification of crypto posts. So there were two parts to the task. So the first part was classification of crypto posts, and it was a hierarchical classification task. There were various categories like objective, positive, negative, etc. And we are asked to classify the tweets, cryptocurrency related social media posts into a hierarchical classification framework. That was the task. And the second task was you have to find out all the answers corresponding to a particular cryptocurrency related question. And for both the tasks, we used LLMs. So this was the dataset, test dataset that we used. The Q&A task had 62 posts in the test set. The Twitter and the Reddit datasets had 500 posts in the test set. And we used both Reddit and Twitter opinion datasets in a 0-shot setting and the Q&A dataset in a 64-shot setting. So the task one is to develop a classification model to classify cryptocurrency related social media posts into 8 classes, namely noise, objective, positive, negative, neutral, question, and advertisement, and miscellaneous. The task 2 is given a cryptocurrency related post, we have to detect all the answers which are relevant to the question. So these are some of the short reasons why you use prompting: leveraging the pre-trained language model knowledge, reducing the need for large level datasets, flexibility and adaptability, improved contextual understanding, and enhanced relevance determination. Next is the methodology. We use the GPT-4 Turbo model via prompting through the OpenAI API to solve the classification tasks. The prompt for classifying the Twitter post was classify the Twitter post into one of the following levels: noise, objective, negative, positive, neutral, question, advertisement, and miscellaneous. Prompt for classifying the Reddit post was similar to the Twitter post. So only we said that classify the Reddit post into one of the following levels and then all the 8 levels. And for the question answering task, we showed 64 examples of title and comment body to the GPT-4 Turbo model. And then we asked the model to classify the comment into relevant or non-relevant categories. Since GPT-4 Turbo has a larger context length, so you could fit those 64 short examples into the GPT-4 Turbo, which probably helped us get better at determining the relevance of relevant answers. And we ran the GPT-4 Turbo model at a temperature of 0.7. For the Reddit opinion task, our score was 0.249 with a rank of 8. And for the Twitter opinion task, it was at 0.249 with a rank of 8. And for the question answering task, our score was 0.157 with a rank of 1. And the conclusion is these findings underscore the importance of tailoring models to the specific characteristics of each task and dataset. And future work will focus on refining the models to better capture the intricacies of social media language and enhancing its abilities to handle a broader range of tasks with more balanced performance across all metrics. Thank you.
Thanks, Aniket. Any questions on the model? No?
The 64 examples, no, for the
Yes.
64 jobs. How did you get to this number? Did you experiment with others or was it just a heuristic decision?
We reached the decision. We didn't experiment with a lot of ones.
And 64 was the best option.
Yeah, so we didn't want it to go beyond a particular context length because the context length is 128K. So we tried fit it into the context length. And since the GPT-4 Turbo has a context length of 128K, so we didn't want to go beyond that because we have to fit in the entire thing within the context length.
Okay, thank you.
Okay, so any more questions?
Do you have a number? I mean, just out of curiosity, like how expensive it is to do 64 shot?
About the cost?
Yeah, because there'll be cost associated like prompt
Yeah.
as well, right?
Yes. So I have to look at the exact cost, but probably I would say given the about 6323 posts, I would probably say it will not cost more than 100 rupees. Not more than 50 to 100 rupees probably. GPT 3.5 Turbo is much less costly. It's much cheaper, but GPT-4 Turbo is more costly. But still, I wouldn't say it will go more than 50 to 100 rupees max.
Okay. Anything? No. Okay. So I have a very short question. So why did you try this opinion in 0-shot mode and question answering in the 64-shot mode?
So initially, we were thinking of just participating in the Q&A task. So we had better preparation for that one. And for the classification, probably we'll future try for the hierarchical classification. So, so our idea was, so for the Q&A task, probably showing more examples would be better. For the classification task, initially we thought it was a hierarchical classification task. So we just tried to see whether a simple prompt will do what level of accuracy can we get. But probably in the future, we will try a hierarchical prompt, like first dividing into the base classes and then bringing the finer classes.
Yes. Okay, thank you. So let's thank the speaker. Thank you. Okay. So our next speaker is Kavya, so from Mangalore University. So, yeah. This is the third time, right? Yeah.
Good afternoon, all. My name is Kavyaji, and I'm here to present the paper titled Navigating Crypto Conversation, a multi-level approach to classify cryptocurrency opinions on social media. The authors of these papers are Kavyaji, Soni D, and H.L. Shashireka from Mangalore University. So here in this, there was 2 tasks. We have participated in the first task, and we submitted 2 of the models, that is unique label LSTM and HCC LSTM. So here about the methodology, first we have pre-processed the given data by removing the URLs, converting the emojis to text. So next we have built the model by using the 2 of the modeling techniques. So here for both of the model, we have used the LSTM, but here we have used 2 of the different things, like for the first one, as we can see here, as we can see in the figure 1, it is a hierarchy of classes. So we'll be having 3 of the levels. So what we have done is like each of the levels classes we have considered as a unique labels. So here, if we consider this as a unique, this is a unique, and subjective and neutral as a one single label, as well as subjective negative as a one label, and subjective positive as next label. So same way we have considered each as a unique label, and we have use the LSTM model. Next, in the next approach, what we have done is like we have used in the first approach, we have used only one LSTM as a flat classifier. Next, in the second model, what we have done is we have used as a classifier chain. So what we have done for each of the levels, we have used LSTM for classifying from whatever it is, like whatever the first level classifier it is predicting, that prediction will be given to the next levels. So these are the 2 models what we have submitted, and the figures classify chains in the HCC LSTM using the LSTM. So this is the figure what we have used for the second model, and the statistics of the data set we can see in the figure 3 as well as figure 4. That is nothing but the Twitter data as well as Reddit data we have got. So for both of the data set, we have used the same models. So these are some sample examples. So what the organizer have provided the data set for Twitter as well as Reddit in the table 1 and table 2. So as in the experiment, we can see the table 3, the first, these are the result of the Twitter data set as well as this is the Reddit data sets. So when we compare the 2 of the proposed models, that is unique label LSTM as well as HCC LSTM, so we have found that HCC LSTM obtained a good result compared to the unique label LSTM. So it obtained a 0.574 and 0.328 macro F1 score for Twitter and Reddit dataset, securing the 4th and 5th rank. To conclude, in the future work, we will be working more on the other learning models for dealing with the hierarchical classification. Thank you.
So thanks, Gabbar. Any questions? Okay. If not, let me ask you a question. So as per your result, your which model is working better, unique or hierarchical?
Hierarchical.
Hierarchical. Yes. And you have applied this LSTM model, right?
Yes.
So why don't you apply any contextual model for this task?
We can apply, but we have tried with the deep learning LSTM itself. So we have found that it is an hierarchical classification. So we were new to this. So we have taken a chance of how to deal with the hierarchy classification. So we consider it as a unique as well as hierarchy classifier. But for both of the things, we have used only LSTM. So we could not apply other things. The last figure, whatever it is, a comparative study of like results, whatever the other participants have got.
Okay, but have you reported the results for hierarchical LSTM?
I didn't get say.
But in your metric, have you reported the result for hierarchical LSTM? Or these are the results on the test data set, if I am correct, right?
This is the test data set. Oh,
I guess it is not.
no, it's a validation.
Yes. So these
Yeah,
results, I
this is a validation because as we have submitted two of the models, only one result we have got it in the like there are whatever the result you have
yeah,
given that
because
is
that
for
is
the
based
test.
on the hierarchical,
Uh,
the model that is working better.
Yeah, for
But
the hierarchical we have got the good result compared to that.
but these are the results on the validation set,
It
not
is
on
the
the.
result of validation set because we haven't got the result for both of the submitted models as we have requested, but
Yeah.
we haven't received it.
Okay.
But it was said like for which run. So we were knowing that which
Yeah,
run it is.
that we mentioned
Yeah.
that on the head.
Hierarchical.
But
it
just
will
a
be
suggestion
better.
that in future you can also try this contextual model for the individual levels, the way you
Yeah.
tried the LS.
Okay.
Okay, thank you. So next is Rudra Roy. So Rakshit Singh, are you here? Rakshit Singh, are you here? Kunal Kushwa? Good afternoon, everyone. Am I audible? So, myself Rudra Roy. I am from IISc Shibpur, and today I am going to present crypto opinion mining, a comparative analysis of hierarchical and fact classification model for social media content. So this is a task overview. There are two tasks. First is opinion classification for cryptocurrency related social media post, where we have to develop a classification model to classify the social media content into 8 different classes, namely noise, objective, positive, negative, neutral, question, advertisement, and miscellaneous. And the second task is that for a given question answer pair on cryptocurrency, the task is to detect whether the answer is relevant to the question. So now the data set for the task one, we have got a training data set of 5,000 opinions from Reddit and 4,987 opinions from Twitter. And for the testing, we have got 500 opinions from Reddit and 500 opinions from Twitter. And the levels were, there are 8 levels spread across 3 levels. The levels were, in the first level, the levels were noise, objective and subjective. And the second level, the levels were neutral, negative, and positive. And the third level, the levels were neutral sentiment, question, advertisement, and miscellaneous. So for the task 2, in the training sample, there are 25,290 question answer pair. And in the test sample, there are 6,324 question answer pair. And there are 2 levels, whether the answer is relevant to the question or not. This is our contribution. We have developed a hierarchical classification framework for classifying cryptocurrency related opinions using Robata-based model. And we have also developed a single level classification framework using XLM Robata model. And for the question answering tasks, we have developed a framework using YLSTM. So this is the hierarchical framework. This is the training portion of the hierarchical framework. So this training portion divided into 3 parts: level 1 training, level 2 training, and level 3 training. In the level 1 training,
we have considered all the text present in the data set, and we have trained a robot-based model to classify them as noise, objective, and subjective. For the level 2 training, we have taken only those posts that are labeled as subjective and trained another robot-based model to classify them as neutral, negative, and positive. And for the level 3, we have considered only those texts that are labeled as neutral and train another robot-based model to classify them as neutral sentiment, question, advertisement, and miscellaneous. And these are the hyperparameters we have used. This is the evaluation, like how this hierarchical framework is going to predict a label for a unknown opinion. So first, the text will opinion will be passed through the level 1 robot-based model. It will classify the opinion into noise, objective, and subjective. If it classifies it as noise and objective, so the prediction process stops. But if it classifies it as subjective, then we will pass that opinion to the level 2 robot-based model, which will again classify that opinion into neutral, negative, and positive. Again, if it is classified as negative, neutral, then we will pass it to the level 3 robot-based model, which will finally classify it as neutral sentiment, question, advertisement, and miscellaneous. And then we have developed a single level framework where we converted the hierarchical into a single level with 8 classes. So for this, we have used Excel robot-based model followed by a 20% dropout and a dense layer. And these are the hyperparameter we have used. And for the task 2, we are given question with their corresponding answers. So we process the question and their comments separately. We use 2 BiSTM model, each for question and one for question and one for comment. And after that, we concatenated the result of the BiSTM and used it for the binary classification. And this is the result. Our hierarchical framework got a F1 score of 0.725 for Twitter and a Reddit score of 0.518, and it ranked 3rd. But our single level classification framework got a F1 score of 0.778 in Twitter and 0.542 in Reddit. That was the best result in the shared tasks. And for the task 2, our BiSTM model got a F1 score of 0.1465, and that got a 2nd rank. And this is the conclusion that our flat classification model performed better than the hierarchical classification model. And the question answering model did not perform well on the test data set, and we will try to improve that in the future work. Thank you.
Thanks, brother. Any questions on this part?
Thank you. The scores overall seem to be not so high, no? 0.7, and you're in 3rd rank.
Yes.
When we look at the literature, sometimes we see higher numbers reported for sentiment analysis, no? Much higher quality. So what is the specific task here? Is it the short text or is it the financial domain? Why are the scores lower here? Is there any reason for that?
So for the second task. Yes. Yes.
Yeah.
Okay, so actually there are multiple classes. There are 8 different classes, and
but only task 1, there are 3, no?
No.
It's
Three
already,
levels there are.
the first it's 8. Okay, you split it up already. Okay.
This is the
Yeah.
This is
Okay.
how the hierarchically the data set was given. The levels were in the hierarchical form, and
if you go to results now, this refers. It's task 1. That means not level 1.
No,
I
task
thought
one,
it's
yes.
level 1. Okay, then.
And for question answering, it's basically still low, right?
Yes,
So,
it's still low.
so do you have any reason?
I think due to the class imbalance, there are more non-relevant comments for a question than a relevant comment. And I think we should use another pretend transformer-based model to improve that task. Or
But the class imbalance problem is quite common. It will have in any kind of data set
Yes.
because relevance are always less than non-relevant.
Yes.
So do you have any idea how to address that?
we can do upsampling. We can use more relevant comments to increase the data set, or we can upsample the data set to make during training we can use a similar number of non-relevant comment and the similar number of relevant comment, so that the model can understand how many
relevant comment and how many non-relevant comment it is going for the training.
Okay. Okay.
Thank you.
Any more questions? No. In that case, let's thank the speaker. Thanks, Rudra. Thank you, sir. So I guess the fourth participant is not here. Anyone is in online? No one is, right? Okay. So Rakshit Kumar Singh or Kunal Kuswa? No, I guess they are absent. Okay, fine. In that case, let's conclude the track for this year. And now we have a tea break, and then we'll again assemble for the conference track presentation. Thank you.
So we are starting last session conference track. So we have a 3 paper, and first paper is from Pritam Pal, bilingual sentiment and emotion analysis, a multitask learning framework for Bengali and English. Okay, so over to the Pritam Pal.
Good afternoon, everyone. I am Pritam Pal from RCC Institute of Technology, and my paper is Bilingual Sentiment Emotion Analysis, a multitask learning framework for Bengali and English. And my fellow authors are Dipankar Das and Anup Kumar Kole. So if we, what is basically multitask learning? Multitask learning is basically a framework that is capable of handling multiple tasks simultaneously. In the field of NLP, for example, it is sentiment and sarcasm, or sentiment, sarcasm, emotion, etc. Task we want to solve using a single neural network. So here is a 2 type of multitask learning example, which is proposed by the Rudar. Actually, the reference is there, but not visible right now. So they propose 2 type of multitask learning framework. One is a hard parameter sharing approach, where we use the more shared layers among the task, and on the top are the task specific layers, which are the task specific layer for different tasks. And another is for multitask learning with soft parameter sharing, where we have each separate layer for each task basically in the soft parameter sharing approach. So next is what is the basically objective of our study. So our objective is basically we want to develop a multitask learning framework that is capable of to identify sentiment, emotion in Bengali and English text at the same time, and we want to analyze how the joint learning of sentiment, emotion can impact the overall performance of the models over there, the single task learning framework. And next is the contribution. So basically our contribution is we develop single task learning framework using the multilingual BART, Muriel and IndicBART models. Followed by that, we propose 2 multitask learning framework. One is the multitask learning with all task specific layers. Basically, we use the soft parameter sharing approach. So we use the more task specific layers rather than the shared layers. And next is the multitask learning with a fusion technique. Next is the data set. So for the sentiment data set, we choose the Sent NOB data set, which is basically social media users content, well, 15,000 samples. And for the English, we provided the Twitter data. We use the Twitter data, which is also a published data, and all the sentiment data set are annotated with positive, negative, and neutral sentiments. For Bengali, we choose the Bangla emotion data set. Basically, this data set is annotated with Facebook's user comment and annotated with 6 sentiment in emotion level: angry, fear, joy, sadness, disgust, and surprise. Next, we extend this emotion dataset to the English text from emotion dataset and Go emotion dataset. So basically, if we see the Go emotion dataset is a multi-leveled dataset which is annotated with 28 emotion levels. But we choose the and it is a multi-level dataset. So first we choose the sentence which is single leveled, and then we filter out the sentence which is annotated with the 6 levels from the Bengali text. As basically we extend the Bengali text to more the Bengali dataset to the more English texts. And here is the data distribution. So this is the right side, left side is the training data distribution, and the left side is the test distribution. So for the Bangla sentiment and emotion, we choose the same data set by their data set authors, basically Saint Enobi and emotion data, and for same as for the English. But for English emotion, as we mix up many data sets, so no official validation but test data set is not suitable for their stuff. So for so how we have done only taken the 10% data from the training set and used as our test split, basically. And next is our simple system framework. So this is the basically single dash learning framework where we provide the here is the basically train data, sentiment trading data, and followed by from the sentiment trading data we have input IDs and attention maps we pass in the multilingual BART, Mudil, and Indic BART model, followed by a dropout of 0.2, and then we have a dense layer, and finally this is the output layer. So this is the single dash learning model where for sentiment classification. And next, this is basically the multi-task learning model. So for multi-task learning, we parallelly use 2 transformer models, transformer multilingual BART, Mudil, and Indic BART, and from both models, we pass sentiment and emotion data parallelly to classify basically sentiment and emotion. And in the fusion model, what we have done, we have concatenated the output of the dropout layers and pass the concatenated output to the sentiment dense layer and the dropout layer of the emotion task to the emotions dense layer, and then we pass the output to the basically output layer. And these are the hyperparameters we have taken to train our models. So we have taken the 256 sequence length. We use the sparse categorical cross entropy loss function. Our dropout is 0.2, and optimizer is Adam, learning rate 2 into 10 to the power minus 5, and 8 batch size, and number epochs we have taken as 5. And this is basically our evaluation. So for evaluation, we pass the test data. Basically, here is the test data available. So we pass the test data to the both transformer models. So basically, for sentiment classification, we pass separate Bengali and English test data to the model, and we consider only the sentiment head, because for the sentiment data set, only the sentiment truth values are available. So for evaluation, the sentiment head is we only consider sentiment head, and we calculate the accuracy and macro F1 score. And we have done same for the emotion classification. For emotion classification, we similarly pass the separate Bengali English data to the models, and we basically evaluated the performance of emotion head, because for the emotion task, only the truth values of emotion data says the truth values are available. So the emotion head's result is valid for this task. And this is the result. So if we see the result, basically to calculate the result, we randomly train the models up to 5 times, because what I can see, basically deep learning models generally produce different type of results in different run. So what we have done, we trained all the models, basically all single task, multitask models, we have trained 5 times and reported the median result. So what we can see for the sentiment classifications, our multitask learning fusion model with Mudil based multitask learning fusion model perform better with an F1 score of 7.71.14 for Bengali and 67.09 for English. And for the emotion task, we can also see the Mudil based models perform better, but in that case, for the Bengali the best result is not that good, only a 39.64, but the single-task model perform better than the multi-task learning models. And overall we can see that the model based models classifies the sentiment and emotions in a text in a better way. And next is the performance comparison. So if we compare our performance on previous work, basically the publishers of a data set, they evaluated the result. So we can see our emotion for Bengali task, our emotion result improves 9.81% with respect to the best classification model, that is the Bengali sentiment classification, Bengali task specific fusion model. We have seen 9.18% improvement, and for the emotion, basically there is 16% improvement. Basically, here is the black. So basically, in the emotion task, we can see there is 16.14% improvement than the best performing framework with respect to best performing framework. Than the basically this is the Rahman ETL. They are the publishers of the dataset. So from their dataset, our emotion classification performance better. Basically, the single-task learning models have performed better. Next is the conclusion. So what we have concluded? We can see the model based multi-task learning fusion model performs better for the sentiment classification, and the emotion classification did not perform well in the multi-task learning framework. Emotion classification basically performed well in the single-task learning, and as a whole, the model based models perform better than for single-task and multi-task learning model both. And next is the limitations. So basically, first of all, the limitation is the limited data size. Only we have choose the 15 to 18,000 samples to train our models. Next is we have limited model exploration. Basically, we have used 3 models: IndicBARD, Muriel, and IndicBARD, Muriel, and multilingual BARD. And we did not explore other models like Debata or XLM Robata, etc. In future, we will try other transformer models, as well as we will try the GPT model or zero shot based approach to enhance our performance. Next maybe we need to do more hyperparameter tuning to enhance the overall performance. And our emotion classification result is not that good, basically only 39% F1 score. So in future we will try to improve the performance for the emotion classification. And one is the major drawbacks of our work. We use the 2 copies of transformer model, which requires more computation power. So in future, and if we increase the number of tasks, then the number of transformer models will increase. So in future, our main aim to develop a multi-task learning framework using a single transformer model, so that the less computation power is required. And here is an example how our models work. Basically, I pass the text as an input to the models, and basically 2 models and 2 basically single multi-task learning models, and here is the output. So if I read the translation, the situation is worse in all the universities, as I myself as a victim look into it. So this test is parallelly passed to both models, both transformer layers, and classified the sentiment as negative, and as well as classified emotion as fear. So thank you.
Okay, next track is on comprehensive dataset and BART models for abstractive summarizer in Marathi by Nikita Kulkarni, Karina Mahagni, Sunita Kulkarni, and Pranita.
Good afternoon. Yes, I'm Pranita Deshmukh. With my co-authors Nikita and Saita, will be presenting our paper, a comprehensive data set and BART modules for abstractive text summarization in Marathi. So agenda for next 15 minutes will be introduction, motivation, the techniques we explored, followed by a Excel sum data set and the methodology we used. Yeah, so we curated a data set for which was specific to Marathi language, consisting of 25,000 plus records, and they were specific to news domain. And also we trained the IndicBART model to compare our data set with the benchmark data set to determine its accuracy. And also this data set is publicly available on GitHub for public use for advanced research. So what motivated us to choose this topic? First of all, limited resources in Marathi language. So there's significant lack of Marathi data sets and robust NLP models. Also, there was a need for domain-specific data, as developing data sets specific to this domain will give accurate results for complex structures in Marathi, and also boosting advanced research in this topic. So the existing techniques we explored for text summarization were first singular value decomposition. Yeah, so it uses principle of dimensionality reduction, and it is one of the earliest approaches for text summarization. Then the BART model, it's a transformer-based encoder-decoder model. So it combines the bidirectional encoding like BERT and autoregressive decoding of GPT, and it's effective for abstractive summarization tasks. Then the T5 model, it is text-to-text transformer model, which basically converts the NLP task into text-to-text format and reframes NLP task. Then the graph-based approaches, so it represents the text in graph representations, and yeah, the nodes represent the sentences and the edges represent the similarity between those sentences. Then the neural networks, that is bidirectional LSTM, which is a type of RNN, and it captures information both in forward and backward direction, making it more effective. Yeah, now Sanita will take over the methodology.
Yeah, so let's explore the methodology part. So I'll give out an overview of the methodology first. So first step was the data acquisition. So we gathered the data for the benchmark data set as well as the data set which we were going to curate. So the next step was data pre-processing, as there is for any data set available. So in that we did some data cleaning, like removing the null rows, and we performed the data start train and evaluation data sets. And then we perform tokenization on the data set using the IndicBART tokenizer, which is specifically trained for Indic languages. And then we defined the hyperparameters for the IndicBART model, which were the same for both the data sets, the benchmark as well as the curated data set. And then for evaluation, we use the row scores. And let's get into the details. For data acquisition for Excel Sum Marathi, Excel Sum is basically a multilingual data set for over 44 languages. And for Marathi specifically, there are more than 10,000 rows for entries for which were gathered from the BBC Marathi websites. And these the summaries which are present in the data set are abstractive summaries. So this data set was used as a benchmark in our research. And for Mahasam, the data set which we have curated, we have manually curated this data set from various
Marathi news portals like Lokmat, Lok Satta, and the total entries in this are about 25,000, which consists of the titles, the summary, as well as the full article. For pre-processing, we did the basic pre-processing, like converting the scraped data and cleaning it into, for making it into a, what we say, apt for the model training. And both these data sets had the title, text, and the summary, which were then added into a CSV file. So for tokenization, as I previously mentioned, we have used the IndicBART tokenizer. It included special tokens which specified that the language which is being used is Marathi. And we also added the padding tokens to make the length of the text and the summaries equal. And the BOS and EOS tokens were also mentioned. As I previously mentioned, the data was split into 80-20 ratio. And for model training, we used a sequence to sequence trainer in a batch size of four and with 3 epochs running. And these were the specifications of the hyperparameters that we have used. And yeah, the metrics would be continued by Mike. Yeah, thank you. So the metrics used by us is row scores. So row scores is very useful for summarization evaluation. So row one is basically comparing the unigrams in both in both the generated summaries and the original summaries. Row two is comparing the bigrams, which is two words at consequently between the generated and the original summary, whereas row L is the longest common subsequence, which is common between both those summaries. So these three scores were evaluated for both the data sets, that is Excel sum and Mahasum. So this is the result that we got, and as you can see, Mahasam has performed better, and we have got more we have got better row scores with the same specifications, hyperparameters that we use. This is the visual representation for the scores. So coming to data set, we can see we have compared both the data sets, and Excel sum has approximately 10,000 samples, whereas Mahasam has 25,000. As Sanhita mentioned, we have done the 80-20 split, and the 20% split is further bifurcated into testing and validation samples. The average document length for both for Excel sum is around 600, and Mahasam is 300. And the summary word length average is 25, and for Mahasam it's 18. So concluding our presentation, we would like to say that we have curated Mahasam dataset, which is the largest dataset that we have in Marathi for the text and its summaries. We have also trained the IndicBART model based on those summaries, which gives us high performance on generating abstractive summaries. And for future implications of our research, I'd like to say that these large scale data sets and models which trained for low resource languages will be useful and will be better for more future NLP techniques. Thank you. Yeah.
Thank you.
Verbo square. ये वाला updated है ना?
Okay, next presentation we have learning query token importance for effective document retrieval with verbose queries by Deepanita Pode.
Hello. ये नहीं चल रहा है? Good afternoon, everyone. Today I am presenting our work, Learning Query Token Importance for Effective Document Retrieval with Verbose Queries. So we all know about Colbert, and those who know in the last talk, Professor Shomen Chakraborty has told about Colbert. So in the Colbert model, what happens is that the query are encoded in queries are encoded using a BART model, and the documents are encoded in the BART model. In the query tokens, all the query tokens are matched with all the BART document tokens, and their maximum similarities used to estimate the final score. So in the Colbert model, they to pad the shorter query, they use mask tokens, and they think that all the tokens are equally important and give this estimate this as a just normal sum. So what is the problem with verbose queries? Well, in the verbose queries, there are several extraneous terms are present. So if we look into these two queries, so Mexico City has the worst air pollution in the world. Pertinent documents would contain the specific steps Mexican authorities have taken to combat this deplorable situation. So I have bolded the terms which are actually important. So if we look into this, we can see that there are other tokens words present in this query also, which is contain specific steps, etc. So when the Colbert model or any traditional model match the document tokens with the misleading terms, which such as specific, combat, so the retrieval effectiveness actually cannot be as per what the user wants. So since all the tokens are considered with equal importance, so for verbose queries, when extraneous terms are present, they all are getting similar kind of similar weightage. So in the Colbert model padded the query with mask tokens. So the authors of this Colbert PRF and a white box analysis of Colbert, they have shown in their paper that mask tokens are similar to the query tokens. So when all the tokens are if all the tokens are if all the tokens are treated with equally importance, so in since the mask tokens are here, so in the verbose query, since extraneous terms are present, so mask tokens will also be there, which will be actually the another representation of extraneous terms. So treating all the tokens with equal importance essentially lowering the effectiveness of verbose queries. So the author's query embedding pruning for dense retrieval. So they remove the query token with highest IDF, but when the query tokens are removed using highest IDF, the code relevant tokens can be missed. So we propose this model where we leverage the pre-trained query encoder and apply a feed-forward neural network onto these vectors of this query encoder, and this weights of this query tokens are estimated, and the weighted sum is done to produce the final score. We for training this model, we use the binary cross entropy loss, and since the
it has been shown that the mask tokens are nothing but some similar representation of the available present query tokens. So we discard mask tokens from this in this model. So for the ground truth preparation, we use the available publicly available trade topics. So in the trade topics, the title, description, and narrative queries are here. So we can see that the title intellectual property, which is basically in the traditional model, we have seen that for title query, it is getting highest retrieval efficiency. So we basically match the title query with the long queries and generate their labels. So this is an automatic label annotation system we have proposed, where we use the where we input the long query words and the title query tokens and output the word weight pair. So for all the pairs, at first we initialize all the labels of these words equals to 0. Then for all query pairs of long query and title query, we first match these query tokens with lexical matching. If they are after stemming, if they are matched, so their label will be 1. We go for all the title words, we get the related words using the wordnet relation and match the long query words with the wordnet. If they are matched, so their label will be 0. And also we use, after that, we use word to vec similarity. If the similarity between the tokens and title token and the description token is greater than 0.5, so their label will be 1. So for training and evaluation data set, we use TREC 678 Gov2 ClueWeb 09B. For test topics, we use the description and narrative parts also. So we use the train topics different from the test topics. So here we are here these are the use test topics and these are the use train topics, and we can easily show that there is no overlap between the test and train topics. We, due to the computational limitations, we use this model as the re-rankers. So we initialize it with BM25 and re-rank the top 100 documents. We overlap the passage using 150. We segment the documents for into overlapping passages of size 150 with strides 75, and for ClueWeb 09B we use the document titles and append it to the start of each passage. And for the model training, at first since we are handling with the narrative queries, which is where the query length should be maximum than 32 tokens, which is the base Colbert model, which is trained by the authors. So we at first we train the Colbert model using the MS Markov passage ranking triples for 500 batches using the parameter given in the original work, and make the maximum token length 225 and queries 64, including the mask tokens. After that, after this training, this is not our models part. This is for this has been done only one time, and we basically use the pre-trained query encoders for the proposed model. So for the proposed model wColbert, we use the input layers 128 nodes for the feed-forward neural network, and 2 hidden layers with 64 nodes each. And we use binary cross-entropy loss, batch size 16, epoch size 15. We use ReLU activation function and add-on optimizer with learning rate 10 to the power -4. So we compare with Colbert models, the base Colbert model that we have trained documents token with 225 document token 225 and query 64 token. We also fine-tune the Colbert model for the specific data set on description query, so that when we are testing it on Trek 678, we train the model for Trek 678 dataset for description queries, and traditional term reweighting models were which basically use the re-ranking thing, means rank the documents twice. So these are the baselines. So this is the comparison. This is the comparison with the base Colbert model. So we can see that our model significantly shows improvement over the base Colbert models, which is trained on MS Marco dataset. And we also compare it with the fine-tuned Colbert models. So we have seen that when the fine-tuned Colbert model, our model is showing expert performance. Later, we compare it with traditional term reweighting method. So here also we have observed that our model has shown our model has outperformed these traditional models significantly. So we conclude that this model consistently perform well on diverse dataset, and it showed comparable performance on fine-tuned models without requiring dataset specific tuning. And we use publicly available dataset, so we don't need to buy any dataset or anything. And the annotation process require no manual supervision. And since we leverage the pre-trained Colbert model and just doing another feed-forward layer on top of it, so it requires lesser training time. So that's all.
Thank you, Deepananda. And with that, I would like to conclude FIRE 2024. I hope you have enjoyed it.
Yeah, like these 4 days, like very knowledgeable for us, and we appreciate your time and your efforts on the work you have done. And we also appreciate that you chose FIRE 2024, and you came to our campus. Like it was like very grateful for us. Thank you so much for your time. Thank you so much.